It's all happened here. Everything we've ever known, done, loved, took place on this drifting, spinning ball that's our home. It's where we learned to provide, nurture, protect, thrive. And yet,
wildfires are scorching the West Coast, leaving behind a path of death and destruction.
Inches of rain this morning.
The waters keep rising, and according to the National Weather Service,
our very success now threatens our future. Today, our greatest challenge is to learn how to grow while sustaining what sustains us. Your understanding, your science, your work are the solution. You have the power to see patterns and relationships and show us how everything and everyone are connected. You have the power to transform how we produce and consume, build and maintain, unite and strengthen, heal and nurture. You can help us see that we can no longer live apart from nature, but must live as part of it. Today, geography matters more than ever. The geographic approach, your work, and the billions of maps you make are essential for creating a more sustainable future.
Good afternoon. Thank you for coming to GIS Day at the College of Staten Island. Just want to make sure you hear me well. We would like to welcome you. This is the 17th GIS Day here at CSI. This year we're doing something different. It's a hybrid event, and we joined with the Graduate Center at CUNY to do 2 locations here at CSI at the Graduate Center, and of course online. I would like to introduce you to Sean. Sean Thatcher has been helping me to run GIS Day events. He is a lecturer at the Department of Engineering and Environmental Science and an Ocean Science coordinator. Did I get that right? Yes. Okay. So Sean and I will be here physically at CSI, and Professor Peters will be at the at the Graduate Center. I wanted to just give you a little housekeeping rules. We're gonna have all of you who are in the webinar format, you're not gonna be able to speak, but you can ask questions in the chat, which we'd love to read out. We have 4 sections for this webinar, and after each section, there's going to be a chance to ask those questions. But throughout the event, please just put them into the chat, and we will guide you to the presenters. All right, so without further ado, I'm gonna introduce Professor Jonathan Peters. As I mentioned, he's at the Graduate Center, and he is a professor of finance here at the College of Staten Island and data analytics. He's in the School of Business, and he's also a member of the doctoral faculty program at the Earth and Environmental Science program and Economics at Graduate Center. So he has a long title. So John.
Welcome all to GIS Day. I hope you're seeing my slides. I'm Jonathan Peters, Professor of Finance and Data Analytics at the College of Staten Island, and Nora already gave me my bio. Speakers, obviously, I welcome you to give a brief introduction to you. Welcome all to GIS Day at the CUNY. This year we're sharing it between the College of Staten Island and the Graduate Center. I put together a bunch of slides that are a basic introduction. People who don't know GIS and don't know why we're all here today, it's nice to just think a little bit about why today is the day. Let's see now, is it listening? It was listening. Machine was listening. Maybe not, so I'll just have to do it by hand. So I'm going to give you a very brief introduction to GIS. Anybody who doesn't know GIS technology, hopefully this will be fun still to look at, even if you're someone who's interested in GIS technology. So why GIS Day? Why today? And everybody who's not in geography should know a little bit about geography. It's the study of the spatial and place distribution of phenomenon processes, as well as the interaction of humans and their environment. There's a bunch of different branches. And obviously, what is GIS? GIS is Geographic Information Systems. It's the way we handle the data of geography. And again, it's a question of when you're looking at where things are and also what things are. We're going to see some good examples. I've already had a little preview of today's lectures, and I think we're going to have a fun day. Given this is an internal event primarily for CUNY, we like to keep it a fun, loose event where people can share their ideas and knowledge with each other and obviously see what's going on the various campuses. And again, in the old days, we didn't have much in the way of this spatial technology. I've been in the quantitative world again for 30-something years. And when I started this, there was no training because we didn't have any of the techniques. So what is it? I mean, what does it actually do? Oh, and why today? Why today? Well, today is GIS Day. Across the world today, there are literally hundreds and thousands of events going on exactly like this, where people are gathering together to talk about GIS. GIS Day is set up in 1987, a collaboration between the National Geographic Society and the Library of Congress and the U.S. Geological Survey to try and promote interest and awareness about geographic systems and how people can use these to analyze different types of information. And Wednesday of Geography Week, National Geography Week, which is this week, is always GIS Day. So every year we meet in the middle of November to be together. Lots of different fields in geography and lots of fields that can be studied by GIS. This is just a few of them. Everything from marine and coastal issues. I was just down in Washington at a national conference on resiliency, how we're going to adapt for climate change. And we're going to see a few examples of that today, but obviously everything from education. We're going to see issues about land use today. I know we're going to see issues about various issues, related to the weather, climate change. And so there's a huge number of applications that can use these technologies and techniques. And the funny thing is I kind of grew into it. I just started doing it. And it's over the last 15 years, it's become more and more interesting to look at different aspects. I've just been looking a lot at remote sensing. We'll show you just a little bit of that. And maybe late in the afternoon, I'll kick in and show you some of what I've been doing. So when we look at geography, we're looking at a few different areas. There's the physical geography game, the human geography. How does humans interact with the world they live in? And then we're looking really at geomatics today, which is cartography, GIS, GPS, remote sensing, all that stuff of how we collect our data and display our data about geography. And then also regional geography, economic geography. So we're here today to talk about cartography, right? And cartography is interesting. When you talk to people about cartography, a map is different than a photograph, right? A map is different than a painting. It's something that's supposed to tell you something about the world. And it's intended to give you some idea, and it may be used for navigation purposes, so you can find out where you are. It may be used to help display information that might tell you about where you're located. But people have been making maps for thousands and thousands of years, and we did it before we could go into space and look down on the surface of the Earth or look on the surface of another planet. And so we were making maps long before we could actually get up there and kind of check ourselves. Well, what's interesting is, how old they are. I mean, this is a Babylonian map. It's actually at the British Museum. I went to see it. I was there and I forgot to take a picture of myself with it. I should have taken a picture with it, right? But that's a Babylonian map. And it has all the elements that we're going to see today repeated in a lot of the work, which is what is actually a map? How does it display the information? Typically, it'll have a legend. Typically, it'll have features that tell you about the world. And if you actually want to get one a little closer to home, I was just down at the University of Pennsylvania, and they have another Babylonian map from Nippur from, 1400 BCE. So this is a 3,000 plus year old map. And if you look on the right there, it will talk to all the geographers real quick because it has a lot of the elements that we typically see. It's got some sort of transportation. They argue whether there's roads or rivers, but there's features such as, mountains or locations on the map. So it really, even 3,000 years ago, we were using the same basic ideas, And again, when we talk about mapping, old school mapping, it was really much more of a or an artistic event. I would be kicked out quickly in this world because I don't have any artistic ability. But old maps are typically done either with drawing or pencils or, painting. And today we're going to use much more map technology. I don't know if anybody here is doing any physical mapping. I don't know in the room if anybody is still drawing maps by hand. I'm long gone. I'm only in technology. But we're going to put together our maps by using things, different elements, and put them together. And we call them layers to build the maps. So for instance, here, this would be like an example. If I needed to look at a new bus map or I put in a new route for a bus, I might draw it first. And then I'm going to code it into GIS so I can analyze, say, where it goes through, what are the demographics of the area that the bus route traverses. I've been doing a lot of work recently on historic data. This is this is the description of a road in New Jersey from 1814. It's all written in longhand, but it has directions and coordinates and everything in it. And that data can actually be converted back and used for a modern map. But in this period of time, I just want to talk to you about what people use to actually, collect the data. Actually, interestingly enough, it actually had a map with it, hand drawn. And on the right-hand side, I'm showing you a photo enhancement of one piece of it. But your old geographers, your old surveyors, they were pretty good. I mean, they actually collected data pretty accurately. As a matter of fact, they were using equipment like this. This is a surveyor's compass from the 1750s. This was your standard tool that they would use. All they had was magnetic north, and they would use a compass, and they would find the direction. And then to get distance measures, they would use this. This is what's called a Gunter chain. And a Gunter chain is a chain that would be pulled along the ground, and it's 66 feet long. They would measure the world in 66-foot lengths. And this is what a survey party looked like in the 1700s. And they would have one person with the instrument and two people with the chain, and they would go around, they measure stuff, and they actually did a pretty good job. So today we're all sitting here with all this technology, but that's actually a map I made using GIS, recreating that exactly 1814 image, 1814 recorded data. And it's pretty accurate. It was only off by about 1,500 feet in 7 miles. So that's pretty good. Even today, we have the other advantage. We can use things like LiDAR, which is overflying the area, collecting the data using laser imaging. This is huge in terms of allowing us to cover large areas of data. And that exact road, I actually have the LiDAR data for. And the LiDAR data, it shows on that, it's labeled A there. That's the actual road. We can take the trees off, and we'll talk a little more about that technology, but we can take the trees off. This is a heavily forested area in New Jersey, and I can, using the LiDAR data, strip it off and still find the road. And what it's finding actually is just a little depression of the road. So there's lots of new stuff coming at us, lots of fun things that are going on. Here's a map that's 250 years old showing the coastline. And we'd say, oh, the old map makers, they didn't know what they were doing. Our new technologies are so good. But the reality is sometimes the old maps are pretty accurate. In fact, in this map, you'll notice Sandy Hook here, which is a feature on the Jersey Shore. And it also shows an inlet marked Shrewsbury. This again is about 1790. You'll notice that looks wrong. I compared it to aerial photography today, which is kind of cool. There's the lighthouse. That's the oldest lighthouse in the United States from 1764. And compare it to the map today, you go, well, that's no good. The lighthouse is actually located where the circle is. Well, the map makers were bad. No, it's not correct. The lighthouse hasn't moved. The topography actually changed in that area. So the old map makers, surprisingly enough, were certainly pretty well-versed in their trade. Sometimes the old maps or orientations are strange and such, like this one, it's horizontal, but if I rotate it 90 degrees, it looks much more like New York City and the Hudson River. It's just that little change in their orientation makes the topography pretty much more reliable, much more interesting to look at for you. Same thing here. This is a map from 1630s. When we orientate it correctly, this is the minuet map. You can see the Hudson River in the lower bay. But we're going to talk about modern mapping. And we're going to use computer technology to do that. So I'm going to introduce our first feature. Again, when we build a map, we build it out of layers today in computer technology. We use some sort of geographic information system to do it. And we'll put together particular layers that show different features that we want to consider in the geographic environment. Typically on a map, and if that map from the Babylonians had many of these aspects, which would typically have a legend, typically have a frame, typically have a title, may have a date on it that'll tell you when it was made. It typically has some measure of orientation, north arrow or something like that, as well as scale to give you an idea of how far something is from something else. So again, I've been making maps now for 15, 20 years, I guess. And this is an example of just some fun maps. These are just fun. This was a motorcycle trip I took in the Baja Peninsula. I tracked myself with my GPS unit and I'm able to remap. And, there's a number of different layers here. There's the highway network in Mexico, and there's my GPS tracks, which are accurate probably to about 3 meters, 9 feet. And then obviously we have the US-Mexican border in green there. And then some sort of a background map here that shows some of the basic layout of the geography. So another example here, some GPS work down in South Jersey. Here, probably about 5 layers of material, including a base map of historical US Geological Survey maps, along with GPS data, as well as information about the ownership of the land. So this is how we do it. We build the maps using the software technologies in various aspects, depending on what we're looking to explore. So lots of reasons to do it. I've been doing a bunch of work in the area for the last few years, and why don't just show people numbers? Humans are pretty visually oriented. We have a very, very strong visual cortex. You'll notice we have 2 eyes on the front of our head. That's typical predator. That's a typical predator aspect. If you have 2 eyes on the front of your head, you're very, very like an eagle or a tiger. They all have these very strong visual cortexes. Therefore, I find map making is very important. I do a lot of public policy work. You try and show an elected official or a community group a bunch of numbers like this, you're not going to get very far, I don't think, in terms of explaining the information and the important issues you're dealing with, versus showing them a map. This is commuting times, with dark blue being long commutes and lighter yellow being shorter commutes. You show this map and quickly everybody can understand and interpret what's going on here. So I found that mapping is a very, very powerful way to communicate information. So we've been doing things. One of the things we worked on early on was we worked on the taxis in New York City. The taxis in New York City are quite fun to look at. There's the origins of taxi trips in New York City. The blue line is one taxi moving around on this day of doing its activity. That's where it's picking up its riders. Here's some data from the taxis. These were taxi trips going, I believe, to the Barclays Center. I have to take a look at it. I believe it's going to the Barclays Center. Where the trip's going to the Barclays Center. And this is the area we put a fence up. This is the actual Barclays Center. We looked at how people use taxis around the city. And again, I think that's in the range of 150,000 records that we mapped to get an idea of who's going to the Barclays Center, where they're going. This is Uber in New York City, mapping out where Uber's active, and that's about 1 million records of Uber activity. So enough of me. I'm happy to introduce our first speaker, Steve Ramaluski is from the CUNY Mapping Service. Is that correct, Steve? I welcome you and I thank you for coming to be with us today. He's going to talk to us about land use.
So my name is Steve Ramaluski, and I direct the CUNY Mapping Service at the Center for Urban Research here at the Graduate Center. I'm here with my colleagues, Will Field and Valerie Bauer. Will actually is going to give a presentation in a little bit, and he'll talk more about the land use aspect in the context of how we're developing some of our maps. But I was going to give a little background about the work that we do in general and talk about 2 examples in particular of recent projects that we've been involved with. So the CUNY Mapping Service has been here at the Graduate Center since 2006, and our role is basically to help organizations, either researchers and students here at CUNY or organizations outside the university, to leverage the spatial data that they have and to help them understand patterns spatially, geographically related to their work, and make that information publicly and widely accessible so everyone can have access to that and understand those geographic patterns. We have created a number of maps and online mapping applications for organizations ranging from campaign contributions in New York City to aging populations and how services are available for those populations, to election results and a number of others. At the heart of our work is understanding demographic patterns, where people live, where they work, what the characteristics are of the populations, and what that means. And so I'm going to talk about 2 projects related to that. One is So for the 2010 census and also for 2020, for the decennial census, we were asked by a national coalition of philanthropic foundations and stakeholder groups who wanted to make sure that there was a fair and accurate count for the decennial census to help them and help organizations around the country that were doing outreach around the census to provide information to them about where communities and where populations were that were typically the hardest to count, so they could use that information to really focus their outreach and educational efforts. And so making sure that there's a fair and accurate count for the decennial census is really fundamental to a huge amount of demographic data, population data that's developed by the Census Bureau and then is used by researchers at CUNY and academic institutions around the country, and planning organizations and community organizations, policymakers. So it's really important to get it right. And so we took information, I'll just zoom in on New York. When we first launched this in 2017, we highlighted information at the census tract level about the hardest to count census tracts that typically did not respond easily or on their own to the census survey. And groups use that information, again, to prioritize their outreach. And then we updated the map with information that the Census Bureau published as the census count was going on in March of 2020, when, of course, the pandemic hit. And so that data collection effort was extended by several months through October of 2020, about the share of households that were responding on their own to the census. And so you could see the dark blue areas are where most households responded on their own. It's called the self-response rate. And the brown or orange areas where much fewer households responded on their own. And the purpose of this information is to get a sense of how accurate and what the data quality is for the decennial data. I can zoom in again. And you can see that there's pretty wide variation in this self-response rate. It's not a perfect predictor of data quality, and it certainly doesn't show actually how many people were counted. The Census Bureau does their best to try to count everyone for the decennial census, but it's harder in some areas, and the self-response rate is a reflection of that. And so it's useful information to try to gauge how the Bureau did in terms of collecting that data, how accurate that data, what the data quality is. And we'll be using this information again, thinking ahead to the 2030 census to try to even more improve what the Census Bureau has done and how stakeholder groups around the country can participate in that effort. And again, this was used by organizations around the country. There's a wealth of information included in this that I'm not going to have a chance to show you, including county by county trend lines for each state to get a sense over time how the self-response rate was, how it differed by area, how it differed based on how the Census Bureau contacted households, whether by mail or dropping off packets of information and expecting people to respond that way. So anyway, it's a really rich, robust amount of data that hopefully is provided in an intuitive, easy to access way. And organizations around the country were very appreciative of this. It was really helpful for their work. And we hope to do this again for 2030. The other example I'm going to show is the first use of first official use of the decennial census data is for redistricting in order to figure out how the populations have shifted in relation to congressional and state legislative districts and also local city council districts. And the process of figuring out how to redraw the lines to make sure that there's equal population for each district and also other criteria are met is complicated, it's political, There's a hearing actually today in Buffalo for the New York State Court of Appeals for a lawsuit that was brought to try to redraw again New York State's congressional lines. So it's very topical. Redistricting is not just a once a decade thing. It turns out it goes on throughout the decade. But because redistricting impacts everyone should really be aware of it and hopefully be involved, because they can, try to communicate to the map makers what district lines make the most sense for each community. But a lot of people don't get involved because their eyes kind of glaze over. They're not going to bother with redistricting. It's some backroom political process. We wanted to open that up and make the information more easy to access and digest. And so we created a series of online interactive maps called Redistricting in You. The idea being that everyone should be involved and aware of redistricting. And so we made it very easy. Let's see if I can do this. We made it very easy to see what your district looked like, what the current districts look like, and how they might change based on a whole series of proposed district plans that had been submitted during the redistricting process. And to make it easy to go back and forth to see how your lines might change. So we provide a tool that you can quickly see. These are the current, or were the current district lines at the time, and how they might change by shifting very quickly and easily from one plan to another visually on the screen. And so you could just see what those patterns look like using GIS in an online interactive application framework. And again, this was extremely helpful. Journalists love this. TV journalists, it's a very visual thing, so they use this for their TV coverage a lot. And it really helped, encapsulate what was happening with redistricting. And we also incorporate a lot of other information about the districts and demographic patterns within the districts, voter enrollment and voter results within the districts, so you can get a sense of what this might mean as far as population shifts. And so anyway, I'll end there and just point out that, these are the kinds of things that we try to do with GIS, again, to get information out there in an easy, accessible, understandable way that is effective and actionable by a wide audience and a broader array of constituencies. So hopefully this is making, putting GIS into the hands of people without them having to know anything about GIS, about how to use the maps and learn from the maps. It's all in there, and pass it along to the next one.
All right. Hopefully everyone can see that okay. My name is Elena, and today I'm going to use a culmination of research from southeastern Mexico to show how we can use GIS in multiple ways to understand this process of regeneration, which is actually a rarely discussed land transformation and sociocultural transformation that does happen in our current age. And happy GIS Day, everyone. And hello, Sean, who is my pal from Rutgers. So today in the Anthropocene, which is this current proposed geologic epoch where human action drives most biophysical changes on Earth, we hear again and again through research, through news, through policy, even through that video that we watched earlier today in the webinar, about the one-way relationship that land use has with our world's forests, where this demand and use of forest resources causes deforestation and degradation. However, there is life in the cycle of forested landscapes after they're used. And this picture shows exactly that. So I took this picture in Mexico. This is the place where I research and learn about forests and also apply GIS skills. And I love this picture because it perfectly shows the complexity of human-occupied tropical landscapes, which are really common across the world. In this picture, we have pastures, we have patches of regenerating forest, we have mature forest cover, we have trees being used for fencing infrastructure. You can see the lines of trees, which are actually fencing infrastructure. Essentially, we have all patterns of forest here. And this landscape spans the southeastern Mexican states of Quintana Roo and Campeche and defines the northern margin of Central America's Mesoamerican biological corridor. I'll call this region just the corridor from now on throughout the talk. And almost 80% of forests here in the corridor are home to communities whose livelihoods depend on forest resources. And they have for millennia, way back to the height of the Mayan Empire. From this time, regeneration in the corridor has been part of agriculture, shifting agriculture systems, where patches of mature forest, multiple ages of regenerating second growth, and land use has made up these complex forest mosaics here. As such, both livelihoods and this important international ecological designation as a biological corridor has depended on the process of regeneration for a long time. And due to the importance of forest cover, both in the corridor, but globally, multi-scale policies are proposed all the time to manage resources in human-occupied tropical forests. And mostly these policies promote simplifying forest landscape configurations, which actually disincentivize these shifting agricultural practices that happen in the corridor. These policies hope to instead separate conservation areas and intensive land use areas. And in doing so, the policies exclude the possibility for real-world dynamics of forest regeneration, which have supported land users and traditional folks across the neotropics for millennia. So in this talk, I'll show a GIS case study from the corridor to talk about why we should go beyond simple policy frameworks based on deforestation or conservation to instead embrace this process of regeneration in the Anthropocene. And to set the context a little bit further, corridor forests face simultaneous and compounding pressures in the Anthropocene, like many places in the world. For example, since the 90s, multiple agrarian programs have created new pressures on forests by incentivizing cash crop agriculture. Just as at the same time, the region is also seeing increased frequency and intensity of hazards such as hurricanes and droughts. This area is right on the coast of the Gulf of Mexico, so we know that there are increasing hurricanes happening right now. And given these compounding pressures, we wanted to see if and how forests were regenerating during these changes, as well as the role of this regeneration for ecosystems and livelihoods. So to complete this goal in examining forest regeneration, we used GIS because going out and identifying all regenerating forest patches is a struggle, and just looking visually at aerial photographs to try to find where forest is regenerated and where it hasn't is a struggle. So we first used GIS to reveal that there are dynamic patterns of forest regeneration in this corridor, this region of Mexico. Second, we combined the GIS analysis and ecological data sets to show that the forest regeneration we found has critical implications for ecosystem processes in the face of global environmental changes. And third, we showed that forest regeneration patterns have critical implications for local scale land uses and livelihoods in the corridor through a community mapping exercise, which we then digitized into GIS. So we really integrated GIS into 3 phases of research. And I'll take some time to briefly outline these 3 different phases of research, but I'm going to spare a lot of the methodological specifics so I can focus on the opportunity that GIS provides, but please email me or send questions in the Q&A. I'm happy to answer anything you have in mind. So getting into the first phase, in this first spatial distribution phase of the project, we classified remotely sent satellite images into forest and non-forest cover maps, and we created a cartographic model in GIS to map spatial and temporal patterns of regenerated forest between 2000 and 2020 from these forest and non-forest cover maps. And what the GIS model did was classify regeneration according to a degree of permanence and when forest regeneration occurred in our study time period, this 20-year period. And this GIS cartographic model showed us that regeneration is happening in the corridor, and it ranges from ephemeral, so non-permanent, to permanent. And also that most of this regeneration is happening in consecutive time intervals that align with the timing of these traditional indigenous shifting agriculture practices. So what's important here is that the GIS cartographic model revealed that diverse forest regeneration patterns are persisting despite agrarian programs that incentivize these permanent land covers of intensive cash crop agriculture and undisturbed forest. We wouldn't be able to identify this with remote sensing alone or going out and sampling from the forest alone. And you can see these patterns in the map here. So this larger dark gray agricultural area actually emerged just after the year 2000, but it exists alongside smaller patches of agriculture and regenerated forest. This large dark gray area is a large cultivation region for chilies. Patterns of forest regeneration around this large agricultural region show that shifting agriculture continues to rotate land use plots into only the regenerated forest patches after a period of time, as opposed to expanding into new forest. However, the cash crop agriculture actually has been expanding through time into the new forest, which kind of discredits this binary that the programs are promoting. So in the second phase of the project, we examined how these forest regeneration patterns become a process that drives forest ecologies. And in this phase, we combined forest regeneration patterns that we mapped in GIS with a 10-year sampling of tree composition and structural measurements. And we analyzed all of these factors together using statistical cluster analysis in GIS in ArcPro. And our goal was to measure if forest regeneration drives recovering tree composition and structure following a Category 5 hurricane that made landfall in 2007. And we found that differences in the amount and type of regeneration surrounding each measured forest stand drives variability in both tree species composition and structure. For example, regions with the highest regenerated forest area correlate with high forest stand biodiversity and smaller diameter, more flexible species that were more resistant to hurricane force winds and damage. So GIS showed us that the amount and type of regenerated forest area has implications for specific ecological processes in the face of increasing frequency and intensity of environmental hazards, like hurricanes that happen in this corridor. So this is a relationship that was revealed through the spatial statistic possibilities in GIS. And finally, we examined if patterns of forest regeneration are considered by Indigenous and local land users at all. So we're saying and thinking that they're important, but are they important to people actually on the ground? So to do this, we interviewed land users through participatory mapping exercises in a case study community. And this case study community has seen the impact of numerous agricultural programs and cash crop agriculture implementation. And also they saw major forest damage from this Category 5 Hurricane Dean. So together with community members, we all drew all over the maps that I created in phase 1. And we added areas that GIS couldn't identify that were of importance to land users in terms of regeneration, conservation, land use, culture, pretty much anything the land users thought was important that I hadn't included. I then went back and digitized all these spatial references from the interviews to incorporate them into my map and see what it all meant. And through this really collaborative GIS exercise and experience, we saw how regeneration becomes a process, again, that drives where certain land uses occur and why. For example, land users described how some agricultural programs deem regenerated forest in regions of shifting agriculture as degraded. And actually, one policy guided folks to establish agriculture in regenerated forest areas specifically. It was actually a rule in the program. However, land users showed a different perspective, stemming all the way back to their indigenous heritage and worldviews, describing that regeneration in traditional shifting agriculture is a means of conservation, and spatial patterns of regeneration support bee populations and pollination, soil productivity, and even microclimates. So folks marked on the map where they continue shifting agriculture because of these services, although it has been displaced now by the agricultural programs to regions farther away in the community. And as a result, integrating land user perspectives into GIS showed us that there is now more forest land overall dedicated to land use of all types, with policy targeting important regenerated forest area. And because of this, overall forest cover and the long-term sustainability of these traditional indigenous land uses become impacted. So to wrap up here, in our research from the corridor, we used GIS in these multiple, independent, very different contexts to identify spatial patterns of forest regeneration. And without the specific tools of cartographic models and the ability to quantify spatial patterns of regeneration, understanding the role of regeneration in this landscape of the corridor would be a real challenge. We wouldn't be able to identify potentially, or it would be more challenging to identify these very small scale subtle changes. Its role as both a pattern and a process really frames the importance of understanding regeneration in the Anthropocene. Specifically, forest regeneration patterns, this land cover class, which is often deemed degraded or lesser than conserved primary forest, through this GIS analysis became an important component for diverse forest landscape configurations that can withstand increasing pressures from environmental hazards, such as regular seasonal hurricanes. Further, this forest regeneration, typically deemed unvaluable in terms of global capitalist economy, was turned by this community mapping exercise into a critical land cover type with implications for local indigenous and traditional livelihoods in the corridor. So I'll end by calling for more GIS analysis of regeneration patterns, but not just limited to forests in multiple landscapes, even beyond the biophysical landscape. We should go kind of beyond and above these narratives of degradation to identify and model real world dynamics that regeneration can provide us in the Anthropocene. And that's all for me. Thank you so much.
Hi again. Happy GIS Day. Thanks for organizing these talks today. My name is Will. I'm a software developer, and I work with Valerie and Steve at the Center for Urban Research. Steve already, I think, gave a good introduction talking about the kinds of things that we do. We look at demographic patterns. So as a software developer, I'm going to try to keep this talk as non-technical as I can, but I'm going to be talking about how the process of building our interactive online maps, and specifically how we've transitioned from proprietary software to open source software. And as a case study, I'm talking about the Long Island Zoning Atlas, which is another project. So we've been working on the Long Island Zoning Atlas for a while, yeah, a year about, and it's getting, I think, close to finished, but there's still, a few tweaks that we're making here and there, but the general, shape of it is here. So I'm going to go through what the map actually does, and then I'll talk about how we built it. So when you load the page, you see this map of areas that are zoned for residential, mixed residential, and non-residential areas. And we're hoping that this is, let me actually take a step back and explain why we're building the map before I get into the details. So the map overall is showing land, what is different zoning ordinances are in different parts of Long Island. And it's we're building it for a few different use cases. There are fair housing advocates who we hope will use this, and developers, researchers. So the use cases are broad and varied. But in general, the idea is to show what is zoned for what kind of residential building on Long Island. So most importantly for these use cases is what's residential. And so first, you see what is zoned for residential and non-residential. On the at the top, we have filters, so you can see what is single family housing only. So as you can see, a lot of this is where single family housing is allowed. And then we have where 2-family housing is allowed and where 3 and 4 plus family housing is allowed. So it's, yeah, you can see it's less and less. There's not a lot here. And then we have sub-filters. So in some areas, certain kinds of housing are allowed as of right. In some places we have, they require a public hearing. So we have sub-filters, and we also have places where you can build accessory dwelling units, ADUs, and some of the different restrictions around that. So a lot of filters, so you can kind of compare different areas. And then we have additional layers that people might be interested in, protected environmental areas, different municipalities. I won't go into everything, but school districts. So all of these are layers that we can toggle on and off. And when you select a zone, so first of all, when you hover over the map, you see different zones outlined in red. You can see some of these zones are, let me zoom in, the shapes are pretty wonky and disjointed. Some of them include streets and some of them don't. But you can hover over them and see the broad outline with some information, some basic information in the upper right, what you're hovering over. And when you click, you can get detailed information for the zone, looking at what's allowed and what's not allowed, and overlapping districts. So if you're interested in what legislative districts or school districts overlap with this zone, you're allowed to, you can hover over these and it'll show you. Okay, so I think that's most of the functionality. There's also, we have search, so you can search by address or municipality to go to a specific place. Okay, so how did we actually build this? So as I mentioned, we've been transitioning from proprietary software to free and open source software. Free, people say free as in speech, not as in beer. So it's you also hear people say Libre. So free in this sense doesn't necessarily mean it costs no money. In fact, one of the things we found out is that nothing is free. Even when you're using open source software, you still have to host your site somewhere. You still have to run machines. But it's open, and it's the underlying source code for the tools that we use is also open. And we've decided to do this for a few reasons. Let let me move this. There's the sort of ethical reasons of having user-directed software. Anyone can adapt what the tools are. We can adapt them to our own needs. It's frugal. It's like I mentioned, nothing is free, but open source we found to be much less expensive, and it's flexible. Again, anyone can adapt software to their own needs, and we have done that for sure. So our old stack was ArcGIS, Microsoft SQL, and then .NET, Microsoft .NET for the middleware and the API to access the data. And then on the front end, we used Vue, which we're still using, which is an open source JavaScript library, and Mapbox, which changed their licensing and is not exactly, it's complicated. So our new stack, we're using mostly QGIS and Postgres with PostGIS, which is just like, it's great. PostGIS is amazing what you can do with it. What I personally have enjoyed about it is that you can dynamically create vector tiles from your data. So you can, if you have access to the database, you can just straight from the database onto the web map, which is expecting vector tiles. And to back up, vector tiles are a sort of a mathematical representation of geography rather than raster information, which is pixel by pixel information about an area. So then for the to connect to the database, our website to the database, we're using Node.js. So there's a nice sort of API library that somebody made and put up for everyone to use. And so I was able to take that and adjust it to our own needs, add some new routes to it, and take, pick and choose parts that I wanted, which is really nice. So let's see, I've already talked about Long Island Zoning Atlas a little bit, so I'm going to skip through here. So some of the challenges that we encountered with the Long Island Zoning Atlas, as you saw, there's a lot of data, and not only is there a lot of data, but it's in every town has its own format that it was given to us. And Valerie did, I don't know how you like. She did magic to make it all work and standardize it, running a lot of Python scripts and QGIS scripts that are above my head. But so the other challenge is some of the zones have a ton of geometry, and it just takes a really long time to load them. And that's still something that haven't found a perfect solution to yet. We're still kind of grappling with that. But we've received paper maps that we've had to digitize, and PDFs, just this one, this is Freeport, where the most recent update was 20 whatever years ago. And yeah, just all sorts of different challenges. Every municipality, I would say, was its own unique challenge. So the digitization process, once it was in QGIS, QGIS can connect directly to Postgres, and you can just directly link the two and put your data from QGIS into Postgres. And from there, as I mentioned, this is the API which connects to the database and exposes it to our website. So we can make requests from the website to the database through this. And it was really nice that this was open source, because I could just, as I mentioned before, take parts of it that I liked and parts of it that I thought could work better. There were some issues with caching tiles, for instance. So I had to come up with my own caching solution. But it was pretty easy. given the way it was built. Yeah, so these are some of the modifications to the API that we had to do to account for some of the challenges we faced. Then styling the map. So we used we ended up using Map Libre, which was before Mapbox changed their licensing agreement. They were fully open source. And so some wonderful people took what Mapbox published and made a fork of it, and it's completely free and open, and it's called Map Libre. The API works almost identically to Mapbox. So if you know how to use Mapbox, you know how to use Map Libre. And Map Libre uses style JSON. So you have a JSON file, which is just kind of like a data format that describes all the layers and how to style them. So we used Matputnik, which again is it's an open source style editor that you can run directly on their website at I think if you just look, I think matputnik.io, or you can clone it and run it locally, and if you need to change the code. And then we have, so Map Libre for the front end. There's 15 minutes. Okay, so just to wrap up, we enjoyed, we've learned a lot through this process, and we've really enjoyed the process of making these tools, and we've found it very useful. So we're using the stack or variations of it for all of these projects and more. And we plan to continue using something similar to it, if not the same thing going forward. So, yeah.
Hello, my name is Maurice Acevedo. As noted, I am a senior in the Urban Environmental Science major in the College of Staten Island. And today I'm presenting a project I've been working alongside with Dr. Jen Alexander, Jacqueline Reisel, and Sean Thatcher. It is on the coastal vulnerability and resistance of the beaches in Staten Island and how they change over time. In our study, we focused on a time span between August 2022 and August 2023. So the reason of the study kind of starts with Hurricane Sandy. On October 29th, 2012, Hurricane Sandy struck the east coast of New York. There were $50 billion in damages, but 19 billion of which were in the city. There was 43 deaths in the city, and more than half of them were in Staten Island. As you can see, Staten Island in particular was very disproportionately affected by this storm in the country, as noted on this FEMA diagram shown. This actually is shown on the FEMA diagram that the city posted in their final findings. So the areas in which we studied are the South Shore of Staten Island. It's noted on the bigger map here. And as shown, we did 12 different transects. And on these transects, we measured the slope of the beach using, the slope of the beach using 2-meter transect points from the offshore ridge to the end of the beach. We used Brunson Transit to record the change of slope between the points using a ranging pole, as you can see right here as reference, as well as we also collected sediments from determined locations throughout the beach, which changed as we did our study over time. Myself, I'm more focused on the morphology of the beach, so I have nothing much to say about the sediment. If you have any questions about the sediment, you can ask Jacqueline Reisel. So this is just an example of the beach profile. This is not exactly the best description of a dissipative beach. However, if you notice the mean sea level from the mean high tide and the mean low tide, there's a dissipative beach will tend to change a lot over time versus a reflective beach, which the South Shore is. The South Shore of Staten Island contains a sandy wave dominated reflective beach. If you notice, even though the beach might seem it's wider, it doesn't actually change over time. So as a result, one may think that it's actually safe to build alongside these coastlines, where on a dissipative beach, one will usually not find heavy construction or heavy building and heavy works. An example of beach like that, as a local reference, could be described as the South Shore of Long Island. If you check, it's mostly beaches. You won't really see anything outside of a lighthouse or a few residential buildings, but even then, those buildings themselves are built for the environment, as in they're raised up above the ground. There's no basements, for example, et cetera, et cetera. You won't find that in older buildings in Staten Island. Newer buildings in Staten Island may be built these specifications. However, I don't have any examples to show of that right now. So after we completed our year-long study, these are the results. This is a sample transect. This is the first transect, which is the closest to the Verrazano Bridge. If you know, there's not really much change in terms of the slope of the beach, and there's not much apparent change in the shape of the beach, which, as you can see here, from mean low tide to mean high tide, not really much change outside of the shape of the beach. Versus if you check here, it could be very variable. So using our GIS, we ended up using a topo over raster program on the program, which interpolates a hydrologically correct raster surface from various sources of data. In particular, we use point data. As you can see from the previous slide, we have elevation data for all the transects, and we use that data by converting it first from lat long to universe canvas or Decatur, that it's easier to manipulate, and using a program that I found online. Didn't really source it, so my bad on that. However, I was able to use the distances that we found between points and input it to this program to show the change of distance and have a fully rounded data set with every point that we took over the 2-meter transects. They all have elevation data. So using that data, I basically made various scope over raster maps, which are shown here, just the yearly data. These are the first 2 maps. As you can see, they're not too informative. They show you basic elevation data based off. But then afterwards, we use the raster calculator, which basically subtracts the values of each point on the rasters that were made with the interpolations, and it gave us the map down here, which shows the change, which can show the change of elevation, which would also be change in sediment load on the beach over a period of time. So this first map shows how the beach changed over 1 year. Not much sediment was added. However, most of the beach did experience deposition of sediment over the year, except for this region over here. There is significant, the most erosion found here. Significant, it isn't as apparent if you go to the beach out there. However, if there were a storm event, those 3 meters could be the difference between flooding in this localized area or not. So using the data, we also were able to show seasonal changes in the beach over the time frame. We did these studies in August of both years, in November, March, and May into June. I kept it to May here for simplicity's sake. For many beaches that are reflective, they have a seasonal change within them. Our beach is wave dominated, so during the summer, there are low energy waves due to the relative good weather in the summer, and it could be noted here. As we can go down towards winter, towards fall and winter, you can see that there's erosion that starts to happen as we go into the winter months, as there is more storms and such over time, and you can see it change right through there. Right. And we consider as marked erosion, especially from November to March. Most of the beach experienced erosion, but as we start going more into March into May, as winter ends and begins spring, you see that most of the beach gains sediment over that time period. However, when we get back to May through August, when we expect that there's going to be sediment that is further accumulated, instead we see that there's a lot of erosion. Now, we can't exactly say why there is so much erosion. We do know that this beach is used during the summer, and we also know that the beach is cleaned during the summer using some of these machines. As you can see, this machine cleans the beach over the summer. I don't know which model particularly used in Staten Island. However, it could be possible that the loosening of the beach space could be leading to erosion over time. However, that's just a hypothesis. After we found this data, we haven't really worked much on explaining the erosion over certain time frames. It's also possible that these areas are also the most used in the beach, so they could be just from people walking back and forth over. In particular, just from observation when we were there at the beach the last time in August of 2023, we saw that there were people around where the most erosion happened. The beach just happened to be open, so it might be a combination of people traveling through the beach as well as the cleaning of the beach, loosening the sediment, resulting in further erosion or more erosion than expected. For future work, like I said, I'm personally doing the morphology of the beach, so most of my work is currently done as of now. However, we still have to process sediments for the sediment analysis of the beach, so that is ongoing. Last I heard, there's a sieve machine that is not cooperating right now, so it might take a little bit of time. We can also improve our methodology by incorporating additional elevation points throughout the beach that are not in the transect, but just at random points, in order to give the interpolation more accuracy. And this will allow us to do a subset of sample transect locations, and using the random points as well, we can do an accuracy assessment to see how accurate the data we have right now is compared to more processed, more accurate data in the future. Okay. And thank you for your time. Any questions?
We're gonna hold the questions until the two presenters present, so please. Thank you so much. John, I'm gonna give back the floor.
Bruce Bell, he's an MS candidate at City College. What field are you in there, Bruce?
In the field of biology. Welcome everyone. It's a pleasure to be here. Thank you for the invitation. Jonathan, I'm actually, I just graduated in September with a master's in biology from City College. So I thought I'd sort of do my best to capitalize on the 3 years of my life that I spent on this, and just present what I found. And it was really had to do with sort of kind of a lifelong passion of looking at tropical forests in detail and what's happening to them. And also sort of marrying the skills that I had. Since college, I remember seeing ArcView GIS and thinking, wow, this is just the coolest thing ever. And so since then I've gone in and worked with remote sensing technologies and of course, and then gone online and done all that. But this is work that that I did with my thesis advisor, Dr. Carnival in the biology department, and she does a lot with, her lab works with biogeography, mostly in the tropics, biogeography and ecology and evolution. I was co-advised actually by someone in the Earth and Atmospheric Sciences at City College, Kyle McDonald, who helped me a lot out with the remote sensing part of it. So of course this is the sort of an overview of the massive amount of sort of Earth observation kind of satellites that we have, and of course this is the European Space Agency puts this out, so they're going to highlight their satellite network. But of course NASA is, and all of the North American satellites are mixed in there somewhere too. But I ended up using 2 satellite systems in my research that I'll talk about in a sec. So all these satellite, it's this massive amount of satellite image and time series data that we're getting from satellites nowadays, when it's trained on forests, really needs some ground truthing information. So we have this opportunity to look at to marry satellite information and satellite data with ground truth data, like hemispherical images and dendrometric data from forests to really come to understand the sort of from a physiological basis to scale these sort of in situ data to large scales based on modeling. So I used actually two different satellites, like I said, and they sample from 2 different regions of the electromagnetic spectrum. Mostly what we know about it, what we see and we interact with every day, is in the visible spectrum, or just near the visible spectrum. The red and in the infrared wavelengths, which Sentinel-2 is satellites are sensitive to. And also I was using Sentinel-1, another European satellite, but it's sensitive to in the microwave spectrum. And really when microwave interacts with surface water on the landscape, then there's a strong backscatter signal. So I'm capitalizing on really these 2 different responses from these 2 different satellites to start to model change in forests. So based on this sort of approach, some previous studies have shown that we can really start to classify or fingerprint tropical forests. In temperate forests, we can already sort of do this and see that and see quite clearly just through optical measurements that the forest green up because of climate change. The spring in the North America is coming earlier and earlier in the season. Not quite so obvious, because since we don't have quite such obvious deciduous activity in tropical forests, because they're obviously evergreen and they don't change as much. But there is, but when you start to marry microwave data, you can see that the changes in the water content in the tissues of the canopy can actually start to profile differences across, for example, the Amazon basin. Up here in the headwaters, where we've got really lush, thick tropical forest, not very little seasonality, very little change in rainfall patterns over the course of the year, we've got very distinct differences in the response from the one satellite and this green one to the microwave signal. So nearly 3 months of difference. As you move on down into the mouth of the Amazon, we've got higher, much more drastic seasonality, a distinct dry season, and those 2 signals seem to converge. Right. So I thought this was fascinating, this approach, and I thought, okay, well, I'm going to use this as a model and start to look really precisely, instead of at the scale of the Amazon basin, for example. I'm going to start to use this sort of fingerprinting, this divergence in this mismatch in the timing of the 2 signals, to really classify on maybe even a pixel by pixel basis in another forest setting. and ask a few questions. For example, what's the timing? Just what's the timing of the green up and the water accumulation? I'm using different satellites than that previous study. And how does it appear? How precise can we really be across a narrow rainfall gradient? That the Amazon obviously is a large one. Also, the rainfall differences are quite large. But let's see how precise we can get. And how does the green up really lag behind this water signal? What is that lag time? And does it actually reproduce different kinds of specific forest classes that we have in another forest setting? So I had an expectation of that the green up would occur later in a tropical forest than in a seasonal forest. That's the optical greening signal. That this lag would be very much larger by extension in a evergreen forest than in a seasonal forest. They'd be much closer. And then a little bit of modeling that I thought this multiple harmonics or harmonics on harmonics were going to be better able to reproduce than just a simple sinusoidal kind of a model. I did it in the Atlantic forest. For those of you familiar with Brazil, this is just this is a coastal. This is on the coast of Brazil in the sort of mid latitudes of Brazil. There's Minas Gerais is illustrated in the interior, and Espírito Santo. In the interior, we have the seasonal forest. There is actually there's a distinct leaf off pattern because of rainfall differences. And then in Espírito Santo, we have a dense evergreen forest. And in these two parks, we've got mostly closed canopies. So I chose these areas because they represent a distinct forest class. Outside these areas, we have sort of a mixture of land uses, which are difficult to sort of parse when it comes to mixtures of competing land uses. So the microwave data again interacts strongly with surface water and also moisture within canopies. And I calculated this index, which is just a mixture of different bands that are information that's coming from the satellite. Same thing for Sentinel-2. I just combining two different errors, combining two different parts of the electromagnetic spectrum, the red and the near infrared, to create another index that represents the greenness. And then I did all of this in a wonderful platform that I came across a couple of years ago, which is Google Earth Engine. And this was the sort of the nuts and bolts and really what brought my entire project to life. So I moved from becoming a biologist to a coder quite rapidly, and realized that I was coming back to my roots and doing a lot of GIS again. Albeit on a cloud-based processing platform, and it was sort of another steep learning curve, but I did my best with that. So I had these two image collections in the cloud, thousands of images that I then created an index for. And then I did something that I thought I would never do. I spatialized. I had this wonderful spatial data set, and then I collapsed them and took a median value and then removed all notion of spatiality. And I got a data matrix. I then took the mean. So I had a time series, right? Moving through time over the course of 3 years. And then I sampled different plots from those different areas. I then averaged those plots so that I got a single value for every time period. Of course, and I had to do some processing to remove some things. But yeah, those are that's the median in the two types of forests there. and I did some modeling of those time series, and I did a single harmonic model. I also tried a multiple harmonic model. I did some of this modeling directly in Earth Engine, and then used some software that allowed me to do some multiple harmonic modeling as well. And this is what how I'm breaking down my signal. I'm looking specifically at the start of the season. This is where the action happens, I guess. And I'm comparing this calendar date across my and comparing that date between my two forest types, and really trying to figure out where this mismatch is happening based on my reference of the start of the season. I looked at amplitude because amplitude is also the degree of variation over the course of the year. It's also important for discovering differences, but my hypothesis really focused on the start of the season. And then I calculated, of course, the differences in the start of the season between these two satellites. And that's that lag that I was telling you about. I did it with the multiple harmonic. Doesn't look quite as nice, of course, when you start looking at this, but nevertheless, the logic is the same. And what did I find really? In the single harmonic model, I find that there is kind of a difference, but it's a little bit earlier in the evergreen forest, in the start of the season. So October 15th is the start of the season in my evergreen forest, whereas the start of the season in my semi-deciduous forest occurs a little bit later. When I use multiple harmonic model, actually there's no real difference I found. So November 2nd is a medium versus November 9th, not too different. So did the evergreen forest green up start later? No, I found that actually it was actually earlier or no appreciable difference. So I'm already coming upon sort of maybe the limits here of my modeling and based on this, but we'll see. And with respect to the lag, we've got a greater lag in the semi-deciduous forest than the evergreen forest, which is kind of the inverse of what I had expected. Multiple harmonic model, again, same kind of trend, a little bit shorter lag in both cases, but nevertheless, semi-deciduous forests seem to be showing a greater lag. So, not what I was expecting. But it was we did expect that there'd be a greater amplitude variation in the green up of my semi-deciduous forest here in the light green. That was expected because seasonality is much greater, so that made sense. When we added a little more complexity, the difference is narrowed, but there was a slightly greater difference in amplitude in the semi-deciduous forest. And this is just so the raw data. This is what the actual data looked like that I was trying to model, and basically trying to demonstrate here that the values in blue are the values of the radar signal, which I thought was sort of the innovative part of my thesis. And it really had a tough time with this period between 2016 and 2018, which were really different. I am recognizing that there's not too many years here to get a pattern from, but it had a tough time modeling based on those first 3 years. And I'm kind of attributing that to perhaps an ENSO event that was a much greater drying period. It was definitely a drier period in the south of Brazil that may have affected the modeling right through. So again, it's forcing a model that will fit the data for the whole time series, which may not have been the best approach. But nonetheless, the microwave picked up on that dry period. So we definitely had a broadleaf green up period that the start of season that was earlier than the semi-deciduous forest. We had a lag that was actually smaller or not significantly different from the semi-deciduous forest. We had a single harmonic modeling that seemed to perform actually a little bit better. Like the simpler was the better approach in differentiating with respect to the amplitude of the seasonality patterns. And again, I was talking about before attributing a lot of these strange patterns in the modeling, probably because rainfall was not constant over the course of those 6 years. You can see that rainfall in this late stage, 2016 to 2021, was actually much lower than in the early period. So if we're actually comparing these the solid bars to the striped bars, the solid bars are obviously in both cases, they're a lot lower in that second period than that early period. So we're witnessing a much drier southern Brazil than we did in the first part of the 2000s. So that may have had something to do with it. So just in conclusion, so we're seeing a lot of with insight explanations of some of these things, probably a lot of with insight variability. We don't have forests that just sort of act the same way because maybe the biodiversity is really affecting this. We've got different trees, different species of trees doing a lot of different things that are hard to generalize on a very small pixel-based scale. We've also got a forest type classification problem, which we might see here. These sort of broad characterizations are difficult to reproduce, and they're often based on some things that are other than physiological response. It's more just basically, is it a dry forest or is it not, kind of thing, but really broadly. But those sort of things tend to be subjective. And this, again, as I was mentioning before, this short-term meteorological anomaly may have been interfering with sort of a more regular phenological pattern. So if that's the case, then this lag approach may be actually a good way to confirm classifications, but I need some ground truth data to really be to really confirm these things.
All right, so good afternoon, everyone, and good morning, everyone on the West Coast. Happy GIS Day. So over the summertime, we had had done a mentoring program with a hires group, which is some high school students and also some RE students at City College. And we came up with this weather analysis and visualization for everyone, known as WAVE. And so basically what we did was look at things that are this new anomaly that occurred. It's kind of like a hot topic with the geology. By the way, I'm an earth and environmental science student here, PhD student, and focusing on geology here at the Graduate Center, and I'm working at City College. So we decided to look at things like subsidence and also inundation, and how can we put these two and incorporate it in GIS for students that have just started looking into GIS, and their first time, they didn't even know what GIS was. And basically that we want to get this information to be able to analyze it, and the visualization for everyone is kind of tell these areas, these people that live in these areas that are in flood zones. And I'll get into that in just a minute. And so basically I wanted to put on there, so this is a part of the hires program. It was between June 28th and August 10th. By the way, I got on board in April, and I was starting in August, and I was like, hey, I wanted to do something. And so I just stumbled across this, and first time I've mentored some students, but I had some good mentors. So it got me into a very, I was kind of prepared, and and I have a love for this. So this was their schedule. So they learned how to do some Python, some remote sensing. So they have somewhat of a knowledge base, and they got 3 college credits while they're in high school. So it's pretty cool for them. And so this how can we display New York City's future coastlines? So what we did was we grabbed some data from from various papers, and we kind of was looking at what areas are like hotspots and what areas have higher elevations. You can see there on the bottom, Staten Island, by the way, has like about 411 to 12 feet, which is the highest elevation in our 5 boroughs. And by the way, out of all the 5 boroughs, only 1 borough is not an island, which is the Bronx. So, so we're going to look at the 2050 and 2100, type of inundation and subsidence in New York City, and we're applying the Archimedes principle, also the bathtub method, and for the following. And so this is some data looking at from mid 1850s all the way up to now, as to looking at 3 feet. 3 inches in elevation from that time frame, and this this varies, and this is just for Battery Park, by the way, in New York City. And so so right now we're looking at New York City has tons of buildings. You're looking at about 1.7 trillion pounds of buildings in the city. So yeah, it does also add to subsidence, and also and the inundate and the sea level rises in New York City is about 3 millimeters every year. And then there's some hot spots, which are those blue dark blue spots there, showing that some areas that are sinking 2 millimeters every year. So you're looking at about a 5 millimeter sea level rise throughout the city when you combine those two. I'm from that area there, from Lower Manhattan, which that area, when I went there during this September 29th inland flooding, it was about about my knees, maybe about 12 to 17 inches of water. Check up on my grandmother, and it was interesting because it was not sea level rise. We're talking about inland flooding strictly, and I was able to see the East River from a street called Houston and Essex Street. It's pretty quite interesting, and this area is pretty much till and artificial fill, loose gravel, or kind of the Earth's crust, and kind of where we're standing here. We're going up high elevation, so here in this area, there was no flooding as much, because as from where we're standing here on 34th Street, you look downtown south, it's going downwards, so the water's kind of going down to this area, and it's reaching to these vulnerable areas, and the area that I was at, it was mostly lower income public housing areas where people still had to go to work no matter what. They don't have the Zoom and luxury. I mean, they don't say luxury, but they don't have the options of, they have to go to work to for these sort of jobs. But so anyway, this is kind of some data that we're accumulating to combine into our GIS. And so this is a FEMA flood zone. You can see in dark blue, and then the other, somewhat of the middle blue is in the 2020s. They're looking about 30 inches of sea level rise in the 2050s. And so basically right here, we're looking at strictly the sea level rise. And these, we're putting all these different types of data, such as ice melt and such, and also the vertical land movements into these projected floodings for New York City. And by the way, this was strictly done by the students. I was like, that they learned through their I was kind of sitting in the classes. I'm pretty new to GIS, by the way, so this is actually interesting that I'm presenting this amongst people that are have been working in this for a while. So it's very appreciate you folks listening to me talking about this. And so this is what they came up. So they looked at two different. They looked at the projection for 2050 on your left, and then on your right looked at the 2100. And you can see areas such as this is Far Rockaway. The darker blue are the regions that are be kind of maybe not around during that time, and kind of going more inland, and then more of our area. And where we're standing right now, is there you're not gonna see much of an impact with these particular floodplains. That's because of the fact that we're on a higher elevation as we go more uptown. For example, City College is 100 feet above sea level. So those areas will be in the clear for the moment. And this is again looking at between 2050, 2100. So this is, I was very proud to see this. I was like, wow, they did an amazing job. And it's the first time they've ever done something like this. They worked as a team, and there was also the instructor of the class that, that helped them out with making these different maps. And basically what they did was just take one map and just kind of combine these layers, incorporating both the subsidence and inundation. And so this, this is just a map showing the climate change's impact on affordable housing, which is something that they were just also doing in terms of kind of a geography manner. And then these are the 8 students, which comprise of some high school students and some RU students from City College and also from City Tech. And they had all gotten together from all parts of the city, and they put this together, and we had a really amazing summer. And that's pretty much it in terms of the research that we've done over the summertime. Thanks for listening.
Richard, don't be embarrassed to be new. I am so excited to see young people picking this stuff up. And the real fun thing is that they can do real stuff. They can do real work. And as a young person, I think it's very empowering to have a technology that allows them to really look at some interesting real phenomenon that out there. I'm billed at the end of the program as talking about some historical data analysis, but I've also just back from Washington, where I was at a climate change and a resiliency conference for the National Academy of Sciences. And I presented on, I know you showed the lower levels of the Manhattan being problematic, but one of our challenges is our tunnels for the subway system. And what's interesting is you have 1 or 2 stations that are low in a piece of the network. So it's real challenging in terms of also the main maintenance yard for the New York City subway system is out in Coney Island, and it's all in the floodplain. So we're going to take a break now, probably 20-25 minutes. Anybody grab we have some drinks in the back. Up here at CUNY Grad Center, people on Staten Island, take a little break. I think Nora is going to present us with the virtual sandbox demonstration.
Yes.
Any of you who haven't seen that.
This is a reality sandbox developed by UC Davis, and it's basically a 3D sandbox. It's interactive. It's a dynamic educational tool to help understand mapping, topography. And we heard about it in our presentation a lot. Watersheds, natural hazards, and more. This tool uses a motion sensor specialized computer software to map contour lines. So actually, I borrowed my kids' Connect that senses the distance from the sand. And when you manipulate the sand, it redraws those topple lines. So just like when you're a kid and you like to play in the sand, right? You can create a complete different photography. This regenerates. Do it slowly, like allow to redraw the isoline, contour lines. And you see water in here because you're playing with it. You can see the water flow so that you can make a valley, and you can see the contour lines redrawn in there. The lighter the color, the taller it is. As you go deeper, the colors change.
No.
And this is, so if you do your hand, you do mimic like a raindrop, you're gonna see little rain developing. And then as you move the sand, you can see where the water would go. It's looking for a deep spot, obviously, a depression, right? Just like the sandy beach. And you can see the water flowing into that area. The deeper you go, can you see the water flowing in? No. You can't? No.
Got it.
I mean, there's a lot of water in there now, so.
Maybe
Let's see if I do this one. I want this water to go into.
Oh, yeah.
There's something in a way. Yeah, you just have to wait. I'm doing it
Look
too
over
fast.
there, guys. That camera is way better.
Yeah, and when you come here in person, I want you to experience. I mean, it's different looking at it virtually than actually touching the sand. So if you are done eating and you clean your hands, the sanitizer, I can't tell you, I don't want this sandbox to be dirty, so. I want to make sure that future users can enjoy it as well. I have the, yeah, right here. So if you want to come up one by one.
So maybe you started at the beginning and I missed it, but like, what is the? Like, I can see that it's fun.
Right.
What would be?
So you helping student understand topography.
Okay, so it would be like a
Learning tool, yeah, it's a hands-on learning tool, so they can manipulate different topographies and how things behave differently, basically. And you can make it very tall. But just to teach about contour lines, right? So if you're teaching a geography class, you want to teach them a lot. Contour lines. Very involved thing. These are the high elevation areas. And I just want to say thank you to Jeff and Caesar. Every year, when we use this sandbox, they want to have, please give them a round of applause. They set it up for us, so it's working. This was a lot of work, and the last time we used it was before COVID, so it's been sitting, waiting for people like you to come and visit the sandbox. So please come up if you're interested, if you want to touch the sand.
I know, really.
Oh, in your hands. Thank you. First brave one. Yeah. All right, come on. I take a long that application did it because it needs to regenerate. This is the water forming. Usually one hand is enough. Yeah, yeah, yeah. So you can use this sandbox, for example, to display the South Shore of Staten Island.
Yeah.
You can see how water react with different, it's kind of how you do.
Yeah. And
So if you're ready, please come up.
Showing my studies in Greenland. We've been going for many years. And what I'm doing there is following the meltwater. When it's created on the surface of the ice sheet and when the sun is shining, and then it flows all the way to the ocean. So at the beginning of the video here, we're on the tundra. You see the stream there? That water is flowing in a kind of a sort of a waterfall. It's coming from this lake. All the meltwater in this lake is coming from the ice sheet, which is there in the back of the video. All right. And I'm looking at the meltwater when it is on the tundra. I'm looking at the meltwater where it's created on the ice sheet. So these are images, drone images from the ice sheet surface. So it's a really incredible place. I don't know, anybody been to a glacier here? Yeah, no? Well, are you undergrads or grad students? Undergrad. I'm going to present at the very end an opportunity where you could join in this summer to perhaps
Can I go?
on an ice sheet, if that's of interest. Anyway, it's a pretty extreme environment, and it's like, why don't you go there? Okay. Well, I think if I can get this to work. Let's see. There we go. I'm going to show you another video too. Have you guys seen this video before? This is a video that's going to run and show how temperature has changed globally since the end of the 1800s till today. So this one will show temperature changes relative to a period that stretches from 1951 to 1980. All right. So we're going to see the colors here represent deviations from that period. So blue and red shows departure. What do you think blue color mean?
Colder than average.
Colder than average, fantastic. And then what's red? Warmer than average. All right, let's show. This is like built on observations, filled in with model estimate. Obviously, there's a lot of uncertainty here in the 1800s, but it's a pretty good idea of what's been going on. So we're gonna go forward. It calculates the average temperature departure in 5-year averages. So here we go. Check this out. So you can see the year up here on in one of the corners, and it just rotates to right. So now we're into the 1900s. You can see it's kind of fluctuating back and forth, but mostly like blue, colder than 1950 to 80. But then it starts to shift here after the World War II. And we're going to reach this. Now we're in that phase where basically the average temperature here is like not changing until we hit the 1980s. You'll notice now that what's really happening is that the whole world is warming. But where do we see the biggest changes? It's even, you notice, right? It's in the far north, all right? And I'm going to show you another image that shows this even more clearly. It's sort of static image that shows the average temperature between in this century compared to the end of the 1951-1980 period. And here you really see that the northernmost northern latitude is where the biggest changes are. And what do we have there? Right there in the middle of North Atlantic, the Greenland ice sheet. This is the second largest body of ice on the planet, together with Antarctica. It contains almost all fresh water on Earth. And it's right there where it's warming the most. What happens if you take a ice cube and put it in the sun? It will melt, right? This is what's going on with Greenland right now. It's losing mass quite dramatically. So often when I open the newspapers, I see information like this. A record melt again and again and again. Sea level loss, rise caused by melting, etc. It's come all the time. Pay attention. And in fact, of the current sea level rise that's occurring right now, the Greenland ice sheet is responsible for almost about 20%. It's one of the largest drivers of global sea level rise. If all of it would melt, it would raise global sea levels with 23 feet. That is like unimaginably large. You here in this part of the world understands what even just a fraction of sea level rise can do. Because if you, I don't know who remembers, but I know some of you were probably here when Hurricane Sandy hit, when Super Sandy hit, right? And that was during high tide. And you had the storm surges that caused so much devastation. Now, this kind of sea level rise won't happen in our lifetime, but even just a little bit. So actually the projections are similar to that difference between the low tide and high tide, just within the next decades. This would just set a new baseline for damages from like a storm of like Sandy. So this is why I need to go to Greenland and other people with me and my team to study what's going on. Because we have the biggest climate change occurring there, and we have this huge block of ice that will increase sea levels everywhere. All right, so I'll show you another. Have you guys heard about a moulin? Do anybody know what a moulin is? It's a French word. It means like kind of sinkhole. I'm going to show you what it is because that's kind of key to my whole presentation. This video here is a film by a Pulitzer Prize winning videographer or photographer from the New York Times who joined at one of our field expeditions a couple of years ago. This shows a stream on the ice sheet surface. All right, this is one of the things I study with my team. this is how most meltwater is transported on the surface of the ice sheet, okay? And you'll see these blue, beautiful streams transporting this water. And eventually this water is gonna reach a moulin, a sinkhole that will take this water to the base of the glacier, all right? And what we need to know, what the thing we're trying to understand in my group is like how much water is entering this moulin, all right? And when do we have most of that water entering? Because both of those things, first of all, it matters for the amount of water that's lost to the ocean, but it can also affect how the ice sheet moves, which also affects how much of the ice is at lower altitudes where the warming is faster and so on. So we want to know how much water goes into these moulins, okay? And this is where GIS ultimately comes in, actually. So we're following the stream. So soon we're going to see that moulin. You see that how it just ends the stream? How it just like terminates? Like it looks like it just goes into nothing. And here it actually, all that water is now going into this sinkhole and probably reaches the base of the glacier and then flows underneath. And the amount of water that goes in and how much at what time has been shown to affect how fast the ice sheet is moving. Because the ice sheet, you can think of it as a river of ice. Okay, so I'm going to show you some data and observations that we've done in Southwest Greenland. So this is a map of Greenland and our study area. And I want to introduce you to my 2023 field team. This is Journey Berry, Arafat Hassan, and myself. And we had a break for COVID for a couple of years, but this time we were able to collect some data. So here's just, and one thing that we've been doing is flying drones, aerial view, launching the drone, Arafat and Journey taking the charge there. And let's see. And what we're mapping is, let's move this. Is this kind of landscape. Look at this, like, it's just like a terrestrial stream. This is like water on ice, but it's establishing similar types of patterns as you see on land, all right? You have this horseshoe bend and all that pattern. So the drones we're using to capture imagery of this landscape to understand like how those streams are oriented and so on. So look at this landscape, it's super fascinating, all right? We're currently working through the data here, but to analyze this drone imagery, GIS is really essential. I'm gonna show you some findings that I've done with two other members from my team in other years. So first, some work by Rohini Majella, who got her PhD earlier this year. This is from a paper that we published roughly a year ago. Okay. One key aspect here has nothing really to do with GIS, and that is quantifying the amount of water that flows in the stream. All right, which is an absolutely difficult thing to do. Because I don't know if you've been to and seen any USGS stations monitoring streams in the US, but those, you put something in, it will stay. On the ice sheet, it'll melt out. So you have to come back and redo it again and again and again. But that data is just, this is a time series of how much meltwater is lost into that moulin. But what becomes really interesting when you can combine it with spatial data collected with the drone. So here is a figure that shows where like our site is, and it shows what we've been able to do by collecting drone imagery is create like a visual image of our entire study area. And then you can use this technique called structure for motion, where from overlapping UAV imagery, you can create a digital elevation model, like in that sandbox, for example, right? You can create a representation of that. And from that, we can understand like how where the meltwater is coming from. So for example, here, this yellow dot shows inland for this particular basin. And then we've been able to like identify where the stream is. This would be impossible to do by foot. Because part of this terrain is really treacherous. There's crevasses. It's difficult. It's like very like up and down. And the white area traces the outline of the area that drains to this moorland. So it's extremely useful. Like, so these are the GIS techniques that we use with the UAV imagery. And it allows us to understand where the water is coming from. So now we can compare, for example, our observations from the field with model estimates and basically be able to constrain where we should grab the model data from. Because understanding all of Greenland's mass loss, it's not going to be possible with observations because it's enormous. But if we can use these type of observations to understand how good our models are, to improve our models, we will be able to, with better certainty, say how much meltwater is lost. Another piece that I want to share with you is a study that I've done together with Sasha Leidman, another a PhD candidate in my team. We were looking also using drone imagery. Let me show you this. This is a little video from our study area. Okay. This is just a drone flight flying along the stream. Okay. Notice how much dark stuff there is in the stream here. All right. You have this like blue kind of beautiful stream. But next to this is Sasha and Rosie actually standing there doing observations. Look how dark stuff there is there. There's actually a lot of sediment and soot coming blown up on the ice sheet from the nearby tundra area, but also melting out from within. Okay, so with UAV imagery and with using GIS tools, we have been able to construct a series of maps to analyze this, the extent of this material. So here we see three figures. The top figure shows the imagery, ortho imagery of the stream, looking down at it. This is the exact same stream that was shown in the video. So this dark area, they were standing like roughly here. Okay. And then we can use tools in ArcGIS and other GIS software to come up with a classification that turns an image like this into a map that says how much is sediment, how much is water, how much is ice, and so on. And with that, we've been able to quantify that in streams in our area, up to 25% of the surface is covered by this dark sediment. Now, why is this significant? Did anybody like take introduction to physical geography or something? Yeah. So maybe you heard about albedo, like the ability of the land surface to reflect back to space. Now, if you have like a white surface, like ice or snow, a lot of sunlight will be reflected back to space. But if you have this dark stuff covering that white surface, it will absorb the solar radiation and it will melt the ice even more. So that's why this matters. And we've also done other studies, basically being able to like identify like where in the channel you see the sediment. It turns out it's in the lower part, in the shallow part of the stream where this sediment can't be moved quickly and so on. So we found out a lot of interesting things by using GIS in this way to look at spatial data. So yeah, I hope that gave you some ideas what you can do with GIS even in really crazy remote places. So my main message is just Greenland ice sheet is like, wow, it's melting fast and it's gonna affect all of us. And the superglacier, the streams on the surface are key to understand how that goes on. And then GIS tools really are essential to understand what's going on. All right, I'll just acknowledge some people in my team. All right, thank you very much.
Thank you. Thank you there. Is Sean ready to go, Nora?
Yes, Sean is ready.
Thatcher is going to speak next, advancing spatial reasoning using a hybrid field course model. Sean, take it
Oh,
away.
I was gonna show that. Can I show one slide more? Yeah.
Absolutely.
Here, guys, all of you who are undergrads, I'm not affiliated with this program, but every summer there's a cool research program in Juneau in Alaska. And it is open for undergrads everywhere. They have stipends available. Deadline to apply is December 10th. If you feel like you want to try that, I think it seems like a super cool thing to do. I would do it if I were you. Check that out. You can ask me. I'll get you the link. If you don't, yeah, or that's the QR code.
Thank you so much.
Spatial reasoning, right? So here we have our location with all students are investigating through different perspectives, leading us to have our mission control group and our astronauts or our rovers to really explore these field sites. What they then do is they acquire different types of data. So our mission control group, right? They are looking at remotely sensed data and they're visualizing data sets in general. Our astronauts are acquiring samples, they're doing photogrammetry, and this is exposing both of our groups to modern geotechnical technologies and are enhancing their ability to think critically about the environment they're in, but also to think critically about the spatial data sets they're providing. This also requires them to collaborate, such as through visual interpretations for our mission control group, along with the field investigations as well. We then require them to communicate their findings with each other, providing them with that large-scale perspective from our mission control group, but our small-scale features that our in-person group or astronauts have. And this provides a lot of flexibility and engagement as well. One of the things that we try to do is not have our in-person students overdo it in the field, especially those of us with disabilities. So it requires them to really think about what they could do in the field. In this case, what they're doing is, and sometimes you might overdo it, but this allows our in-person students to switch to our virtual cohorts, especially when problems arise. Next slide. Now, this is not as easy as it sounds. It's just like running a hybridized event. Sometimes there are kicks. Now, some of the things that we have can be broken down to 4 main categories, right? Technological, social, time, and other, right? Our catch-all. Now, platform compatibility here is the biggest problem that we have, especially who's using Macs, who's using a PC. Not everything works well in Macs, not everything works well in PC. Sometimes they hide the button and we don't know where it is, right? Also making sure that our technology can work on both platforms, which is always a problem in general, right? We also have issues with background knowledge. There's a lot of information that goes into understanding the San Francisco volcanic fields in Arizona. So, if you've never had a volcanology course or a planetary science course, if we're looking at other celestial bodies, it gets real challenging. Other issues that we have are analysis paralysis, right? And I'm not talking about my physical challenges, right? I'm talking very specifically about we give them an overwhelming amount of data, right? And in this case, what happens is that they don't know when to stop, right? So this is why in some cases my students currently know this, like, no, you've done it enough, now we write. Okay, for those who finish your master's and your PhDs, you know that as well. From a social perspective, collaboration between our in-person and our virtual cohorts is a big challenge. If they're in person and there's limited communication in the field, they cannot communicate with our virtual students. Likewise, our virtual students spend a lot of time in front of the screen during the day, and we need to take that into consideration as well. Spending 13, 14 hours a day is not exactly conducive for a virtual learning environment. And this is something that we're actively working through as well, especially because we've accepted students that are from coast to coast. Okay, so time zone challenges have been a real pitfall for us. Other issues have been, external responsibilities as well. And then in our catch-all other, right, power outages have actually been a huge problem for us. In person one year, we had 3 power outages in Florida due to tropical storms. We also had a power outage in the field as well. I was on the second floor of the hotel power went out. I was like, how do I get downstairs? So it was a really fun experience for everyone. Fortunately, no big problems. Others are scheduling. As any of you know, any type of scheduling for events, programs, it gets really challenging to do this, especially across time zones and when traffic is a problem. Others are employment obligations. One of the reasons why we have a virtual group is because some students cannot travel because they cannot leave their jobs, but they're important. And these are things that we're actively working through. Now, from a professional development perspective, next slide, this has been a huge opportunity for students. So in some cases here, what we have are professional development, how they connect their understanding to volcanic processes, collaboration, data collection, spatial interpretations, and mentoring to presentations, right? We have a lot here, but I'm going to try to read out some of our big findings from some of our surveys in general. So students here have not only developed a deeper understanding of volcanic processes by incorporating spatial reasoning. So for example, one student really said, in JMARS, I could explore features at my own pace and learn how the appearance of features can be altered by formation or after formation, right? And this is really important for our students, not only connect these processes, but really being able to make the connection between the data they're using and exploring at their own pace. This is in JMARS. We can also do this in ArcGIS and other technologies as well, which we're currently in the process of revamping. Synthesizing presentations encourage critical thinking and enhance engagement in a professional setting. Our students have done wonders in regards of presenting in national conferences. Feel free to scan the QR code at the bottom right hand corner. Check out the Geospace Resource tab in general. One-on-one and group guidance encourage deeper understanding and build confidence. Many of the mentors and instructors role modeled how to think about the data we are looking at. I now feel like posters and conferences are totally doable. And for my students that were just looking at the Geological Society of America conference, that's entirely realistic for them. They're really gaining the confidence to not only persevere and present their work, but also to be the role models they not only may not have had themselves, but really to be the role model of institutions and programs they might not have had as well. All right, last slide, I promise. But just some 5 key takeaways here, right? Hybridizing experiential learning experiences promotes accessibility while developing these spatial reasoning skills in novel ways, right? We are not diminishing academic rigor. In many ways, our students are leaving not only with the ability to do their own work by looking at terrestrial analogs and engaging in field type, really being able to communicate and share that information with the broader public. Incorporating our mission control impact on learning model enhances field type analysis and interpretation, along with collaboration. Just like today, we are running a hybrid, and this is really the way that our field is moving. Being able to work in a hybridized environment is important for your professional environment, right? So that really bleeds into our third takeaway as well. Challenges exist, but flexibility promotes new ways of engagement, right? There's not one static way to do anything, and for those of you that do GIS, you know that one button will not always work, and sometimes you need to partition it, break it into different parts, do a lot of other things. And this model has provided students with the confidence to undertake research efforts on Earth and other planetary bodies as well. Now, this is not done just by me. This is a collaborative effort. Next slide. We have faculty members that are presenting not only from the University of Florida, myself from the College of Staten Island. We have others from Central Connecticut University. A friend of mine who just started at the University of Hilo as a tenure track faculty. I'm feeling really excited. Another one of our instructors actually just began working at NASA, along with the other colleagues with tenure at Arizona State University and Fuller University as well. All right, I'm a liar. I have one last slide. Okay. Thank you again for listening to my talk on enhancing spatial reasoning, utilizing the field course model. If you are interested in applying for the GIS-based field program, feel free to scan the first QR code. And if you want to follow us on X or Twitter, because I still don't refuse to use it, feel free to scan the second QR code. If you want to follow me on X, feel free to scan the third QR code. And shameless plug, if you want to check out my own personal website, it's the 4th QR code. Right. Thank you everyone so much. And I'm going to answer.
Any questions from the audience here? You have like a tip for how to get selected for this program?
Yeah, if you're my student, talk to me about applications. Okay, I love applications, especially when they're not mine, right? Also, if you're thinking about applying for the opportunity that Osa shared, talk to me as well. That deadline is coming up in the beginning of December. Okay, and for those of you that are in the Earth and Environmental Science program here at the College of Staten Island, you remember the internships to graduate. This would count potentially. Okay, so really keep that in mind. If you're interested in applying, definitely come and reach out to us and talk to us. We have our application that's live on our website right now. Feel free to Google us in general. If you're trying to find us in general, you can always Google the GIS-based field program and Anita Marshall, which will lead right to our website.
I'm going to thank you for that introduction. I'm going to be talking about a study of flooding from Hurricane Ida on Staten Island. And first I want to point out, everybody should know this. Each hurricane is different Katrina 2005 was different from Camille in 1969. Sandy 2012 different from Irene 2011 and Ida 2021. If you look at the tracks here, here's the track of Sandy. Sobel and Hall came out with it's a 714-year track, and that does not mean it occurs every 714. There's, I think, a 0.14% chance of occurring any one year. Now, Sandy didn't have a lot of rain. See, let me just go one. See that? You look at the rain here for Sandy, you hardly got anything, but you got a lot of storm surge, 14 feet. Irene came up like this and dumped a lot of rain on us. And Ida, you see the track like this and the rainfall here, and you could see over here how much it came through. So the moral of the story is each hurricane is different. You can't go by one for the other. Now, there are different types of flooding. There's coastal flooding that we had with Sandy. There's fluvial type of flooding, which we don't really get here, but you've seen it around the country with big rivers. My hypothesis is that it's fluvial flooding, and I'll go into that. And then there's compound flooding, which could have all of these. What two, or it could have coastal and rain and fluvial. Anyway, here's what I got out of the references right there. Surface water floods occur when a drainage system is overwhelmed, and that's what my hypothesis is about Ida. So look, we had to go back here. If you really want to understand flooding on Staten Island, look at the 1896 streams on the footprint for the DEM. And here, I would say a good part of these streams are no longer there. But we have mountainous areas here, and you know what's going to happen? It rains, the water would have gone into the streams, and then out to either to the Kilvan Col or Arthur Kill. Now, our Messonet station on Building 1R recorded this for Ida. It was a storm that started around here, say about 4 o'clock on September 1 and ended about here somewhere. This is the cumulative rainfall, so we got 8.44 inches of rain. But more importantly, look at these dots. These are 5-minute rainfalls. The one up here, it was raining at 7.32 inches an hour for a short time. And here's 1.6 after that and right before it. So we had intense rainfall, and our drainage systems could not handle it, our sewers couldn't handle it, and catch basins. So I went out the morning after in the dark to look at what's happening, because during Ida, I had the FDNY frequency on, and I couldn't write down fast enough all the rescues that were going on. And they gave the amount of water. Now here at this place where the Costco parking lot is, I counted 17 abandoned cars here, and one had a plastic barrier on it. So you can conclude the water was much higher. When the water receded, the one went there, and so forth. So we have signs like this that may be good. And I have a sign here. The one over here I got from down south. And I've been advocating for these signs around New York City and Staten Island. We need to know how much water is there. So when you have a staff gauge with the road may flood sign, you can figure it out. And you'll see that every day. It'll be ingrained into your mind that that road can flood up to 5 feet or something. And then I went to Richmond Hill Road. I counted 3 cars here, and they were left there overnight when the floodwaters were there. So again, I advocate for those signs. Now, from the Staten Island Advance, our MTA bus depot is over here, and they had a picture like you see here with cars floating. So I went back and I looked at it. It's the same place. You can see the building, sort of, you have the white building, this building, and then I started to look around, and I put a meter stick there. So that water was over 3 meters. And then, so the city came by after Ida, they put these road may flood signs, but they don't have the staff gauge. Okay. So if we look at the area here, I'll just show you, here's Richmond Avenue's here. Here's Forest Hill Road, the Costco is over here. So I plotted where these cars were, and here's the Costco lot over here. So my hypothesis is that, guess what? Our streets became streams. And the water went all the way down here where it formed, 5 or 6 feet of water, according to the fire department. And I advocate again for those signs. So I pulled together all of this material from New York City, opened the 2-foot contour lines, 1896 streams, New York City stormwater maps. Interesting. These maps came out pre-IDA in May 2021. And I would look, I'll show you some of them, how you can, it sort of will sort of agree with what happened in IDA. And then I have some LiDAR, DEM, streets, lots of blocks, catch basins, and wetlands. So let's look at this. So here's a DEM of the area, and I plotted all 19,000 catch basins on Staten Island. But I didn't do it by hand. I went to I hope where it's still be here now. And so it's high here and low here. So it's going to rain here. The streets become streams, and we have the 440 highway here, where the water goes down, and there were streams here at one time, but they're gone. And we have a little and the highway is sort of elevated so the water can collect. And we'll take a look at this. And also we had flooding here in the Port Richmond area. You can look at the map here. It's in the northwest part. So I plotted here these 5 houses on lots, or 5 lots. The fire department came there after IDA because their basements got flooded. And this little line is an 1896 stream that was not here at the time. So I put things together. I put the blocks and lots. I put the contour lines on here. I put the streets again and everything. And then I plotted it here. And those 5 houses are right over here. Now the blue here is the New York City stormwater map data from May of 21 before IDA. And we still have it 80, and I plotted this 1896 stream here and so forth. So here's what I found out. Okay, now, when a contour line crosses a stream, everybody here knows what happens. The V of the contour line points upstream. But you could apply it to streets because you have a 2-foot contour interval. So if you look here, so that would be upstream or up street, and the water came down here where it's supposed to. So the flow is like that. So you're gonna. So I started to do it's a work in progress. I'm going through Staten Island and going through this with the contour lines and so forth. So you could use the 2-foot contour lines, well, you wouldn't be able to do it with a 20-foot type contour line, but you can do it with 2. And then in the area here, now our college is over here somewhere, but if I plot on the street here is Victory Boulevard, and the May 2021 stormwater maps show these areas get flooded, and they did. I found out that there were all kinds of cars abandoned here during IDA, and the place here flooded out, and so forth. Here's the Staten Island Expressway. So we're over here somewhere. So then I looked at the westerly area where they had tremendous flooding because the highway is elevated here. These are the 1896 streams, which would have drained the whole area out to the Kilvan Cove. So I looked at this, and I found a contour line here, which is so similar to the box over there. Only the contour line here has hash marks on it, which are depression contours. So as you go in, you go down instead of up in a mountain. Okay, so it's a 30-foot contour line. And the map is a 1966 map, photo revised in 81. So anything in purple came after 66 and before 81. They urbanized what's over here. Now, they did have the streets in after, but I started to plot all the streets here. Now, this triangle, again, the fire department reported over 5 feet of water here. And that's where this was over here. So we have the street here. Here's the Lion Place and what's called Devon Street. And here's the 1896 streams which would have drained out the whole area, which are no longer there. Okay, so then I plotted here. Here's the information before Ida, May 21, the New York City stormwater maps. Deep and contiguous flooding greater than 1 foot. Look at that. So, okay, so if the streams were here, I would have hypothesized that they probably would drained out the area. And if also you urbanize an area, you put concrete and asphalt down, you stop the inflow, you don't have the infiltration, and you again decrease the lag time between the rainfall and the runoff. And I plotted the contour lines again. I wanted to look at this. The blocks and lots are here, and so forth. And here's the 1896 streams. Okay, and then I plotted here from New York City website the stormwater maps from May of 21 before Ida again. Deep and contiguous flooding greater than 1 foot. We knew it was going to happen. It was published by New York City months before Ida. Okay, so we have that. And then if you look at the DEM here, so here's the, I'm talking about the region over here. Here's the 440 highway. You have high ground here. It rains on this. The streets become streams. The water collects right there at the base of the 440 highway. In fact, I went there the next day, and here's a car that got floated, and it's, you know, it sort of indicates that it was reoriented. Let's put it like that. Now we do have the blue belts on Staten Island, and here's a blue belt map. So you might ask, well, what is a blue belt? New York City DEP had a what they did here. They took existing streams that were there, and they used them to manage the stormwater with BMPs, which are best management practices. So here's that. And I on the same footprint, I plotted the 1896 streams, and you can see the ones that are gone are up here, as you could see. And here's all the different blue belts. We have them on Staten Island. We're very lucky to have them. They did manage the stormwater during Ida and Irene. And then I put everything here, the streets, the blue belts, the streams from 1896. So anyway, Ida on Staten Island was due to pluvial flooding when the sewers and so forth couldn't capture all the stormwater. Anyway, I thank you for your time. Also, we have a FloodNet team, and I'm in it with the group here. This is for the future. We are putting sensors all over the city, especially on Staten Island, which will sense if you have a flood. Okay, so it's a work in progress. We have a few of them in already, and so forth. So that's the future. CSI FloodNet team. Okay, I want to thank you for your time, and
Thank you, Alan. Appreciate it.
Hey, hi, hello everyone. Okay, I hope you're all having a great day and enjoying the presentation so far. My name is Elia Machado, and I'm an associate professor in the Department of Earth, Environmental and Geospatial Sciences at Lehman College, and also faculty in the EES program and the EEB subprogram at the CUNY Graduate Center. It is a pleasure to be with all of you today, and I'm looking forward to your comments and questions at the end of this talk. So I'm going to start by providing a quick overview of my research, just to set the context of this presentation. And that is that 95% of lands, terrestrial lands, have some indication of human activities. And this is according to a paper by Kennedy Rowe in 2019. In this map, you can see the percent of human modification across the globe. And now, whether 95% is accurate or not, the fact is that humans have drastically transformed Earth, and that is widely recognized. And it is also widely recognized that the impacts of those transformations in ecosystems, human livelihood, and health are becoming more widespread and severe. So the question here is, what can geospatial methods do about this? And this is the overarching theme of my research. As a human environment geographer, I focus on the development and the application of geospatial methods to examine the interactions between social ecological systems and global environmental change. By global environmental change, I'm referring to both systemic changes that operate globally, and an example of that will be the emission of greenhouse gases. And the other is more localized changes that cumulatively have a global impact. And an example of that will be land use change. More specifically, I focus on three aspects of global environmental change. One is the characterization of that change and the monitoring of that change using, for example, change detection methods. The other one is assessing the vulnerability to the impacts of that change, and particularly in the context of environmental hazards. And the third one is the identification and assessment of potential mitigation and adaptation strategies for global environmental change. And this is the focus of the presentation today. All right, and this brings me to the guiding questions of the study that I'm going to present, which is, can social safety net programs aimed at reducing poverty and food insecurity help mitigate global environmental change? And this is part of a paper that I published with my co-authored Kalle Hirvoven, Andrew Simons, and Vista Ras in the Journal of Global Environmental Change. And this work was funded by CGR. First, a little bit of background, since I suppose not many of you know about social safety net programs. In general, the term social safety net is used to refer to programs that provide in cash or in kind aid to lower income households. Now, in Ethiopia, the social safety net program is called PSNP and is a public works-based program. And what I mean by that is that those cash or in-kind transfers are provided in exchange of work. And that type of work could be in many different type of work, for example, restoring community assets or natural resources. And an example of that would be tree planting, right? Now, this is not the only type of programs of this kind by any means. It is estimated that about $10 billion with B dollars are spent annually on this type of programs that employ about 70 million people globally. So this is big, this type of programs. However, most of the research has focused on the social impacts. And that makes sense because it's the main goal of these programs, right? Now, oops, I didn't mean to advance the slide. So now we saw an opportunity here to look into what are the environmental impacts and potential benefits of these programs, right? And so more specifically, what we do in this paper is to estimate the impact of the PSNP in tree cover and also to see its potential carbon sequestration benefits. Here's a little bit more of details on the program. It was launched in 2005, and it is one of the world's largest and longest running programs of this kind, with about and now surpassing 8 million of beneficiaries. And as I mentioned earlier, the objective of this program is to relieve poverty and food insecurity. In terms of the public works, these include social and water conservation and reforestation activities, among others. So you can see that there is an environmental focus also part of this program, right? And what I'm showing in the map are the areas that participate in the program. These are depicted in this kind of brown color. and those that do not participate in this kind of light beige color. And the areas on white are those that are not included in this study. So we use different kinds of data, a lot of remote sensing data in this project. The main one that we use is the percent tree cover. This is known as the VCF product, and it is from MODIS. Okay. And then, of course, we needed the administrative boundaries of Ethiopia, right, to look into the different areas and districts. Additionally, we used the PSMP documents. These were provided in paper from where we extracted the beneficiaries per year and at different administrative levels. And then a series of other variables that I'm going to explain later what the role is. These include population density from the gridded population of the world dataset, elevation, land cover, right at the onset of the program, which was in 2005, annual rainfall data from CHIRPS, and then above ground body biomass density, which was used to estimate the carbon. And the main method that we use to estimate the impact of the PSMP in tree cover is known as the difference in differences regression method. And basically, the idea is to estimate the difference in the percent tree cover before the program started, before 2005 and after 2005, and also in the district that participated in the program and those that did not participate in the program. Now, an important assumption of this method is that the districts that do not participate in the program and those that do participate will follow a parallel trend through time, right? Now, this assumption was not satisfied for us, and therefore we have to apply another step to find the districts that were comparable, right? So that we can compare ecologically the district that participated and not participated in this program to see the change on tree cover. Here is a little bit more of detail on the methods. Basically, as I mentioned, we started with paper reports for the PSMP. This was a lot of work to extract the numbers from these reports into a tabular format so that we could have the number of cases, meaning the number of beneficiaries on this program by year, district, and region of Ethiopia. Then there is the VCF dataset. As I mentioned, this dataset actually includes different variables, and one of them is tree cover. So you have to extract this variable from the dataset first, and then do a lot of processing, process the flags, the quality flags that come with this dataset as well, and to identify the pixels that do not include or do not have tree cover, meaning, for example, water and so on, just to exclude them from the analysis. In terms of the land use, land cover, this product is also from MODIS, and we aggregated it into 5 categories, and I'm describing the categories in here. The digital elevation model, we generate a slope from it, and also sliced the slope into quantiles, and you're gonna see why in the next few seconds. And then from the gridded population of the world, we did the same thing. We thresholded it into different categories. So once we have all of that done, we process the Ethiopia administrative district and regions. And I think that anybody here who has worked with administrative data through time is very aware of the pain that it is when you realize that some of these districts are going to be split or merged or so on, and then you have to deal with that mess, right? I mean, that's how it is. So a lot of time was spent here to come up with a homogeneous layer based on the 2007 benchmark. And we picked that one because it was the closest to the latest census from Ethiopia. And the closest to the beginning of the project, which was in 2005. So once we have everything established, we joined everything together so we could have the data set to start the analysis. We identified the pixels in the PSMP and the non-PSMP that were comparable to satisfy the assumptions of the difference in differences method that we apply. And then we run the analysis, first with the pixels from here, then stratified. And stratified meaning, remember how I said that we stratified the slope into different quantiles and also the population density and so on. What we wanted to see is if the impacts of the program in tree cover vary according to slope or the land use of the beginning of this project, or according to population density. So this is why we run this analysis in different kind of stratified way, right? And then there was a lot of robustness and sensitivity tests that we did as well. Lastly, using these results, we use the above ground woody biomass to estimate the carbon benefits of this project. All right. So this is what we found. We found that the tree cover increased 3.8% in the district that participated, and this is controlling for rainfall and during the duration of our study period, which is 2005 to 2019. And as expected, we also find that this impact was not homogeneous over space, right? So we find that, for example, there were areas that had lower density of population, meaning more rural areas, right? Had a change in the tree cover that was higher. So this will be less than 150 people per square kilometer, right? And as we increase the population density, this impact decreases, right? And the reason for this is because this program targets the poorest areas on the country, and those typically are more rural areas. So this finding makes sense. The other finding that we found was just like the impact of the program in the tree cover was also higher in areas that were steeper. So as the slope per quantile increases, we also see an increase on the estimate on the impact. However, you can see here that there is a moment where it decreases. So this really intrigues me. I think there is a moment where the slope is too high to even plant a tree in there, right? But here the logic is that many of those slopes are the ones that are target for reforestation because they are more prone to erosion. And the other thing is that many of those are also available for reforestation because they are not used for agricultural uses. It's too steep, right? And then finally, we have here the different categories of the land use land cover type before the program started in 2005. So areas that were classified as forest are the ones that also had a higher increase in tree cover. And I think this makes sense because, well, we are trying to reforest and to build a forest right near area that already are forested. Oh, and I missed one as well. We also find that the district that had a larger number of beneficiaries in the program with respect to the whole population also had a higher increase in tree cover. And these are our results in terms of the carbon sequestration and the benefit cost analysis of this. So one thing that probably is not going to surprise you, right, is like we did the estimate according to the years that the number of trees that the trees will be planted and there, meaning stayed in the ground, right? So of course, as the number of years increase, the benefit cost ratio also will increase, right? And I don't know if you know this, but Ethiopia actually had a climate change plan and participated in the Paris Agreement and many other strategies for planting trees and many others that are related to this. So when we estimated this, we also find that the annual negative CO2 emissions right, that could be reduced, were equivalent to the 1.5% of what Ethiopia's pledged on the Paris Agreement. We'll have to see how that turns out, right? And then finally, we also made calculation based on the cost of the program, right? So, of course, if these trees were there for eternity, the social benefits, right, could offset about 49% of the program annual cost. Now, this needs to be taken with a very big grain of salt. And we discussed that in the paper, right? Because these are very crude estimates. We didn't take into account, for example, the type of species that could be planted, right? Among other things. And here are the conclusions of this. So again, I mean, can social safety net programs such as like the PSNP, right, help mitigate global environmental change? There has been a lot of discussion on this type of programs that could be, you know, kind of like a win-win solution, right? Addressing the social issues and addressing the environmental impacts. So in a way, yes, I mean, our results are very encouraging. However, we know, and it has been documented in the literature, that these type of efforts are challenging, right? And one of the aspects that needs to be considered when we are trying to do this work is that it needs careful planning and really integration. I don't know why my slides are advancing like this, sorry. It needs careful planning and integration of both the biophysical activities, meaning, okay, the selection of the species and so on, but also the social context in which these activities are happening. I mean, you need the support of the communities there, right? And don't forget what is the main objective of this program. Further research is needed in terms of the scalability of this, right? And potential trade-offs. And also, well, I'm looking here and I've presented our result in terms of carbon, but it's important to not lose sight of the important benefits that trees provide, right? And the restoration of natural resources. So there are many benefits that are not just carbon. And then finally, we document the study limitations and the results of the robustness test in the paper. So if you are interested, I can provide you with a copy. Thank you, everyone.
I'm going to be quick, but I want to just go over a few of the topics. Okay. Okay, so it's giving that prompt. Okay, the title, which has been moved around, I don't know why, which is Identifying Historic Roads in Southern New Jersey. It's published in the Proceedings of the Transportation Research Board of the National Academy of Sciences. You can get a full copy of it. Also, if you're interested in finding some data and techniques, there's a bunch of links in that paper, as well as we have an annotated technical documentation that goes along with it. So if somebody has an interest. You seeing everything, Nora? Yes? Good? Okay.
Yeah, good.
So roads are one of the earliest form of human modification of the environment. We've been doing them for thousands and thousands of years. There's lots of reasons why you want to understand where historical routes are. In addition, there's a lot of fights about who has the right to access land. We have this idea in the West that people own the land and then people try to exclude others. This is a Western phenomenon where people try to exclude other people. In the case, they have actually two pieces of public land that touch at the corner, that they will not allow someone to cross the corner. So there's a big fights that have gone on where people try to stop people from crossing from public land to public land across the corner of the property, because it's a square piece of property. So again, there's a lot of discussions about access and about use. So when do you want to look at roads? There's lots of different roads. This, of course, is the classic Silk Road, the Oregon Trail, our historic routes. The Oregon Trail still exists. If you go out to Western United States, there's still sections of it, never been paved, never been modified, pretty much look like they did in the period that it was used from the 1840s to the 1850s. In a lot of cases, the area has been worn by the traffic from the wagons from the period. Lexington and Concord, the road from Boston out to the fighting, that's still preserved in some places. And I'm looking at an area down in South Jersey and particularly an area in the Pinelands, which is a largely undeveloped section of the state of New Jersey. They have a number of historic roads in there. And I used to say good pirates. I use the term high quality pirates now. I'm going to tell you a little bit about the pirates of the state of New Jersey during the Revolutionary War. And again, they were high quality pirates. They were authorized by the government. They're called privateers. If you were in the Revolutionary War, it was much better to be a privateer, which you would go out and attack the British ships with a private sector, because if you captured the ship, you get to sell it and you'd make money. So these are actually roads that still exist down there. There's 4 roads illustrated here that are in the forest that have never really been well documented. They've never been paved, to my knowledge, and they still exist pretty much as how they were in the 17th century, 18th century. So I'm using new techniques to analyze very, very old things. And again, in the early part of the United States history, you didn't really want to travel by land. Land was lousy. It was full of bugs and animals, and the roads were poor, and traveling by water was the preferred way. The only reason you went by land was if you didn't have any money. But they also had a lot of smuggling. The Americans have never liked to pay taxes or do the things according to the rules, and the British imposed taxes. And the Americans, even before the revolution, started smuggling. Then the war comes, the Revolutionary War comes, and the American army and the populace were short of materials, and so they started privateering. As a matter of fact, they appointed a guy to be the head of quartermaster. The quartermaster is the person in the army that gets the stuff, the goods, the materials for the army. And the guy they appointed was a guy named Nathaniel Greene. Nathaniel Greene said, I'll do it. He didn't want to do it, but he says, I need 2 people to help me. And the 2 guys were John Cox and Richard Pettit, and they were both privateers. They were both well known to be involved in the smuggling trade. So they actually would take and capture the British ships off the coast of New Jersey, and then they would drag them inland as far as they could, because you didn't want to unload the ship and bring it further by land. So you'd bring it in on the water, you drag it up the river there to this point called the Forks, and then you'd unload the cargo, and then you bring it over to the west to Philadelphia. Also, you would bring stuff up to Valley Forge, the famous terrible winter of Valley Forge. They were short of goods, so they would route around the northern route. And these roads were used by those privateers at that time and moving the cargo. This is actually a publication that was saying that they were going to sell pirate cargo, and they would publish in the paper when they captured a ship what they were going to sell. And this is the great ship Venus in 1778. They grabbed it and brought it in there, and it was at that location right in the center of New Jersey that they were going to break the ship down and sell off all the cargo. So the question is, how do you document it? Oh, by the way, this is a letter from George Washington to the privateers to say, hey, I'm short of stuff. Could you help me out? I'm looking for some extra special stuff. There, he says right there, he knows it was brought into that point. So can we use some techniques to identify roads? And one of the things we want to do if we have a historical asset is you want to identify it and then preserve it. And one of the typical things you do is put down into what's called the National Register of Historic Places. In the National Register, you have to have some documentation. So how do you document something that just exists in the forest and doesn't really have any physical, has been documented in the past? How can we identify where it is? So that's what I did. The first thing is you can look for a number of different ways to do it. You can look at historical maps. You can look at historical documents. You can go there and recreate the actual routes using GIS. And then you can do field analysis. You can collect data using remote sensing, either using GPS units or using things like LiDAR to get information on what these physical assets are. So when you look at early maps, some of them are really good. I talked about it earlier today. Some of them are not so good. I'm not going to spend a lot of time. Some of them were not very good because the people who made them just would copy other people. I was out at the American Association of Geographers. If you've never been there, it's in Wisconsin, Milwaukee, Wisconsin. They have the largest collection of globes in the world. So when you go there, it's a heck of a library to visit. But they said, oh yeah, everybody copies everybody else. They don't make a new map. They just copy the old one. They don't bother to go out in the field and collect the data. They just copy somebody else. So during the Revolutionary War, there were people in America who were fighting for the British, but their families back in Britain, they wanted a map of America. So somebody would just knock off a map, no matter how good it was. So some of the early maps stink. They're really bad. This is an early British map, and it's lousy. It doesn't have really good spatial relationships and all this. So the things I'm actually looking for are these. These are the roads. That's what they look like in the forest. And you notice the road actually has what we call a holloway, which is when the wagons and carts would go along it or vehicles go along it, they carve out a little bit of a depression in the forest floor. And in this case, it's about 8 or 10 inches high. So they still exist that way. And what's interesting is how crisp they are. Like they don't really, people don't vary outside the line of the road. You notice they just, it's pretty, the edge is pretty sharp. That's another example there. Again, so you again can get new maps and you can compare your maps. I'm not going to spend a lot of time on that and see how well it lines up with existing aerial photography or existing maps that are out there. Another thing is that they would make a document up when they would put a road into place. Now, what would happen is you would put your road, say, show up at Farmer Jane, and you'd say, hey, look, we're going to take the road, the county road through your property. She would usually agree without any problem because her property became more valuable because her property now is on the county road. And so she could get her goods to market quicker. And anybody who buy the property would say, oh, good, I'm on the road. That'll be useful for me. So they would put together a document called a road return. And my brother's a co-author with me on this, and he's a land surveyor and civil engineer. So it's good to have somebody from a different field because I'm an economist. And I said, where's the deeds for the road? He says, no deeds. Deeds don't exist for roads. He says, there's a road return. They would write up a letter in the county courthouse and you'll have a record of the actual document. And there's the stack of books down in Burlington County. And if you pull out the documents, it'll look like this. And by the way, that is my thumb on the upper left-hand corner of this document that was dated 1798. That is the original document that they were letting me use. And of course, it's all in longhand, but it has coordinates just like we're used to. And it actually is, this is the road return for the purple route that I'm showing here. The original document from 1798. So the dark purple route in the middle. And what I can actually do, these routes are actually recreated. I take the coordinates out of the original documents. I transcribe the documents, and then we can remap them in GIS. So there's a modern map of the historic road created from the original 1798 document. Now, again, it's one of the problems is you have to figure out where they actually fit because you have the coordinates of the road, but you don't know where it starts. Well, I'm kind of lucky. So in this case, the road we're going to talk about is the orange one, the Quaker Bridge Road. It has a rather distinctive L on the end. You see it on the right there. And it's like, you have to nail it down. So we actually get the coordinates and I have the dimensions of how far to travel and what degrees to turn and all that. I have to find a starting point to nail it to the physical geography that today. The good news is, it actually, in this case, one of the problems you run into is you try and match things up, like field names of places have changed in 250 years. So what we do is, in this case, I'm very lucky because it happens to start at a point of a very prominent location, which is that square thing, that square object there on the ground is the actual original boundary marker between the east and west sections of New Jersey. And that's where the road return started. So I went out there with my field GPS units, and I surveyed where that was. And so that's why I had the coordinates to start the road return. The funny thing is, there it is. That's the boundary marker. And then I can realign the road. The funny thing is I also went out and tracked on the exact existing roads. And you see the purple dots are the GPS data collected in the field, and the orange data is the recreated data. And they're pretty close for 300 years ago. And again, people were working with very, very old technology. It's probably more accurate than it appears because the coordinates have to be adjusted for the magnetic north of the pole. And over 300 years, the magnetic pole has varied. So I should really be adjusting. I'm still messing with that. So again, there's the road based on the road return. There's the GPS we call breadcrumbs. And again, I showed you this earlier. There's the field equipment they were working with. That's the compass from 1750s. There's the chain, and they would go into the field and they would hack it through the forest. They would hack what's called the road center line. And people in engineering know the term road center line. The road center line, they did it once. They went through the forest once, and they'd say the road is two chains wide, 66 feet wide, 2 chains on either side. They'd only go through once. They didn't want to go through one side of the road and then do the other side of the road. So there they are. That's what they look like in the field. They still are that way, unpaved. There's the transcription. And then again, the roads are set up typically. There's another example here. Sometimes they have a map, which is really cool. You can take a look at the original map. That's I get the original map. A lot of them are faded, so you then photo enhance them, and that helps a lot looking at them. And again, I can then line them up. So I also then recreate the actual data using GIS. And in this case, this road is 7 miles long. The deviation at the end, I'm pretty close on the beginning end. It's off by 1,500 feet over a 7.5 mile run, which is pretty darn close. And so more than sufficient to document the location of these assets. The new technology, the new technique, I'm not going to go into GPS. I track it with GPS, of course, is LiDAR. And LiDAR is an example where they overfly. And by the way, people are interested in this. Most of the area of the United States has been flown already. I just download the data. In this case, I've gotten it from New Jersey State government agencies, but they also have a web server. It's in the paper. There's a web server that shows you. So what is LiDAR? We fix the data. We fix the location of the plane using GPS technology. So we know where that plane is. And then they shoot the ground with a laser beam. And it comes back and bounces back, and it tells you a bunch of different point elevations. And the last one, the bottom one, is the ground. And everything else, it might hit a tree, it might hit a house, it might hit something else in the air. So the data is actually collected, millions and millions of data points are collected using LiDAR. And then what we do is we process it. I take the data down and I process it. So in my case, there's another example of the truth. So what they do is the data is massive because it's lots and lots of data points. So they give you a tile map because they take it in little pieces. You have to look at it kind of in little chunks. So you get a tile map, and then you pull the data that's appropriate for what you're doing, and you pull your particular tiles. I mean, you get it first down, it looks like this. And that's just what's called a point cloud. Now that's all the elevation data. Now, again, this is a heavily forested section of the state. And so you then can process it to only look at the ground. So these are the ground points only. And then you can use the technique, if you're using your GIS software, to create what's called a TIN. It's a triangular irregular network, which is basically it joins all the data points into the nearest 2 points, because that's the simplest physical flat surface you can create. And so it triangulates all the data points, and you can process the data to get this. Now, what you're seeing here is you're actually seeing that one road I found, A, which I was showing you I recreated. There it is in the forest. You can actually pick it out. It's actually elevated in that case through a swampy area. On the other side, B, you can see just a little bit of a trace of another road. Some of them are pretty narrow. If they're narrow, they don't show up as high, but you can usually pick them out. D is what's called a oxbow lake, where the river went by. The river goes by in the south there. The dark blue is the darker part of the Mullica River. That was a section that got cut off and actually filled in. And that's called an oxbow lake. And then you had a few canals floating around there. But again, the LiDAR data is accurate to about probably 6 to 8 inches vertical. So I can pick out some rather subtle things in the actual background. So there's what it looks like in aerial photography, and it's a pine forest. So it never de-leaves. Some of the new techniques I've seen of people using drones, using aerial photography. This is a little rough for those because it's a pine area and you're never going to get an area where you can actually see the ground. But LiDAR goes right through it. Again, pretty darn accurate, pretty darn interesting. Here's another section of that road. Again, looking at a different section. You can see, by the way, you can see a lot of terrain here. You're seeing some of the flood zones. We talked about Alan Benoff. We also talked about, Ilya talked about some of the issues related to topography. You can clearly see it. This is pretty flat. Southern New Jersey is pretty flat. So it's got some pretty interesting water features. What this does is, in the end, the portfolio of work I've been doing is you have multiple ways of identifying where a particular asset is. I've got terrestrial GPS, I've got historical records, I've got historical maps, I've got LiDAR data, and I can reconstruct the road using the historical data. All those help you to give a better picture on where something is. And obviously, if you're going to try and document something for preservation or for recording it for future use, it's real neat to have all these different methods. In some cases, you have all 5. Some cases you don't. I happen to have most of them here. So that's what I've been doing. And I'm finishing up. Why is this stuff kind of important? You know, when you talk about historical places, usually have stories about them. There's probably the most famous trader in American history is a guy named Benedict Arnold, and everybody in grammar school learns about Benedict Arnold. Well, what you probably don't know is he got himself in trouble down here on those roads. He commandeered some wagons, and he got brought up on his court-martial. And there's good suspicion that those roads were part of the reason he got himself into trouble. And so it actually documents a pretty interesting part of history. Once he's court-martialed in 1779, he's a tragic, you go back and forth. Every day you do something different with Benedict Arnold. He's bad one day, he's okay the other. But that was the beginning of the spiral downwards. He gets into trouble with this using some wagons from the government. And he was part owner of a ship called the Charming Nancy, and he got himself into trouble. And that was the beginning of end of Benedict Arnold. Just for fun, the Americans hate him so much. When you go to West Point, they actually have a plaque to all the generals of the American Revolution. His is on the lower left with his name obliterated. They wouldn't put his name in there, and they also don't have his date of death, arguing that he should be in hell forever. But Benedict Arnold was there, and he was a player in this region. So it is a part of American history that is pretty poorly documented. As a matter of fact, they actually published this court martial, and it has information about the wagon masters using those roads. And so that's what I'm doing, is looking at how I can document these facilities for preservation purposes and seeing where they actually are. So it's really cool. And there I am on 4. I have a couple of minutes. So with that, I'll thank everybody for joining us today. It's great to be involved in GIS. I hope you can have some questions for us. Please feel free to reach out to us. The members of this panel, as well as the members of the organizing committee, are more than happy to talk to you. We hope you get involved, and we hope to see you next year. It'll be on a Wednesday in November. That's when GIS Day is. Thanks so much.